Communication Engineering from NIT Patna in 2002, an MTech in Telecom Engineering from NIT Durgapur in 2007, and a PhD from IIT Patna in 2016. He has published several peer-reviewed research papers in journals and conference proceedings. His area of research includes wireless communication, underwater sensor networks, device-to-device communication, and microscale energy harvesting. He has over 20 years of experience teaching at the undergraduate and postgraduate level. He is presently serving as an assistant professor in the Department of Electronics and Communication Engineering at NIT Jamshedpur. He is a senior IEEE member and a life member of IETE and ISTE New Delhi, India. He is the principal investigator of two sponsored research projects in the area of underwater communication. He has successfully organized several sponsored faculty development programs and delivered invited talks at national events. He has visited several countries and participated in reputed international conferences. Let's give him a big round of applause and welcome.
Thank you so much for this nice introduction. Yeah, I can say it.
Yes, sir. Never done first.
Just look at the fear. Extremely. Most recently,
Yes, sir. Yes, sir. Yes.
We can start now, right?
Yes, sir. I'll start showing
So, very good morning to all of you. As my introduction, I'll give a presentation on computer vision. Okay, it's going to be a discussion about sensors and computer vision that we use in robotics. Okay, when we talk about robotics, it's a very huge area. There are so many people working in it from different regions. Okay, it's different areas of research. And if you think about robotics, not just mechanical engineering or electronics or any other, it's a combination of a large, in fact, a very large domain. Okay, we have electronics, we have mechanics, we have electrical, we have chemical, also sensors and all those things. Basically, we operate in the chemical industry. So, in my presentation now, I'll talk about sensor and computer vision applications. Okay. Now, I'll just begin with a very simple thing. You know, all of you were very much conscious about sanitizers, okay, or hand wash. This was a very important term some few months back. It's not
it was streamed in
okay. So, if you remember, sanitizer and hand wash, they were very important things, right? And if you remember a simple hand wash, you have to push, you will get the detergent or the hand wash, and then you can wash your hand. Then came an era in which we had automatic hand wash, no touch hand wash. Okay, so what you do, you just take your hand beneath the hand wash dispenser and you get a drop of hand wash. Okay, so how that has become possible? The earlier case, you had to push the hand wash. There was some push type of button type of thing you used to push and you used to get the hand wash. Okay, so that was a very simple machine. Okay, it was a machine. Why it is a machine? Because it is programmed. It is made in such a manner that if you want a drop of hand wash, you will apply a force. Okay, and each time it will give you almost the same amount of hand. Okay, so that was a machine, and when you give it a vision, that is when you take your hand beneath the dispenser, you get a drop of hand wash without touching it. You get my point? So if you think about giving vision to a machine, you are making it smart, you are making it autonomous. Okay, so you have to give it a vision. Are you getting my point? Like human beings have vision. When someone approaches you, you give something. In the same way, we want to give vision to our robot. Earlier, the robots were not having vision. Okay, not having exactly the same type of vision we have. So we'll now begin with our PPT. So this is the outline of my talk. I will talk about human versus robot. Okay, we'll just compare. I think some of these things may have been discussed earlier also. Okay, so it will be a kind of revision maybe sometimes. So we'll just begin with a very brief history about the humanoids. Okay, basically earlier we were making robots to replace machines. Okay, we were trying to make smart machines. But now what we want to make robots which will resemble human beings and would perfectly replace a human being. That is what our intentions are, and these days we have got many such robots also. Okay, then we'll talk about sensors in robotics. Okay, human beings, we are very much intelligent, very smart, just because we have a lot of sensors. We can sense that that person is sad. Okay, we can sense that this is hot or this is cold or air pressure is high, low, like that. So we have a large amount of sensors, and of course we cannot compare it with the quantity of sensors the robot can have. We have extremely large amount of sensors, and sensors are also guided by our experience. Okay, sometimes maybe a person by touching can tell what is the temperature. Maybe another person by seeing can say what is the temperature. Okay, if you talk to a person who is cooking, he may not touch and tell you what is the temperature. He will tell what is the temperature without touching. Okay, so we will talk about sensors in robotics. Then we'll talk about vision in robotics. I begin with the very good example I told you about the soap dispenser, automatic soap dispenser or detergent sanitizer dispenser. It has got vision. Okay, so we'll think about how to give vision. Vision not only means our eyes. Okay, it's not just related to eyes, right? Then the third thing we'll talk about, because we are here to discuss about research and other things. So we'll talk about market trends in robotic vision. Okay, why this domain is becoming so much popular, why people are investing money in it, okay, and why we want to research in this area. That is another point. Then we'll talk about high speed vision sensors. Okay, as human beings, we have a limited vision capability. Okay, you cannot see something which moves very fast. For example, if someone shots a bullet, you may not see the path. Although in the movies they show that the bullet is moving and revolving and is going ahead, human being cannot see them. Okay, so how it is possible in the movies? They make it in a slow motion. They capture it with very high resolution camera, and then they show you in a slow motion. So you see the bullet moving and then hitting the target. Are you getting my point? So as human beings, our vision is limited, and what we want high speed vision sensors. Okay, we'll talk about that. Then we'll talk about latest technologies in machine vision. Okay, what are the technologies that are being used? Then we'll talk about electronics of sensor. Okay, if you go to the root, each sensor is basically uh, a transducer that generates some kind of voltage or current. Okay, every sensor. So we'll talk about that. Then we'll talk about a little bit about digital image processing, which is quite specific because it is a particular area in which people do research at a higher level. Okay. We have to do digital image processing. Every day we do that. When you take a picture in your mobile camera, you have many apps and many tools. You can edit your picture, you can enhance the quality and things like that. So all those things come under the domain of digital image processing. Okay. But remember, image processing is a passive domain. Okay, you can make an image clear, you can make it very visible, but you cannot extract what is the information in it. It is not something related to intelligence. You can take an image, you can rectify it, improve it, okay, make it very good, you can make it very visible, but you cannot know directly what is the story inside. We'll just talk about this also in one of the slides. And then we'll talk about robotics in driverless car. Okay. See, in the research domain, we always put emphasis on what is the most popular thing. So today, if you think about the industry, what the industry is trying to do, you will see so many cars are there. Okay. And what the industry is trying to do, industry is trying to change those manual cars into automatic cars. Okay, these are happening step by step. Some 10 years back, we had gearless cars. You don't have to change the gears. Now it is coming in the market. Okay, in India also now many gearless cars are coming. In the same way, some 12 or 13 years back, Google launched the driverless car. Okay, and over the period of time, now it has been permitted also. In foreign countries, you can drive the driverless car. Okay, in India, it's not yet officially allowed, but you can have a driverless car. Okay. It says that the driver must be seated. You can have a driverless car, but the driver must be seated. Okay. So we'll talk about the robotics in driverless car and we'll see how all these things are used in. We'll see how all these things will come into picture when we take a case study of a driverless car. Then we'll talk about the research opportunities in this area. Okay. See why we are here because we want to do some kind of research in this particular area of robotics, IoT, sensors, right? We all intend to do something new. Okay, we want to contribute something as engineer or as scientist to the community. So we'll talk about the research opportunities in this domain. Okay. So there's a very simple comparison. You might have seen it earlier also, maybe in this program also. Someone else might have shown. So here what we are doing, if you look at it, it's very simple to understand. We want to imitate a human being by making a robot. So if you want to make a human being, it should resemble all those things what a human being has. Like if we begin from the top, human have a brain, so we need a kind of controller, some processor, some kind of a computer. Then eye is a sensor, so we need sensor in our robot also. Then we have muscle, so we need actuators in the robot. We have arm, so we need arm, robotic arm. We have hands, so we need end effectors. Okay, then we have legs, we need some mobile mechanism. That means something which can make the robot move. Okay, this is a very simple comparison. I am not showing all the things, but there are many other things, right? It's not just a sensor as a eye, right? Our skin is a sensor. And this is just a rough comparison, but it will give you a preview why we want to compare humans and robot before we go ahead in the discussion. Okay, now this is a very simple enumeration of some of the facts that compare a human and a robot. Okay, for example, a human and a robot. So robot must have mechanical movement. Okay, There must be power generation and storage, like we have mechanical movement, so we must have mechanical movement in the robot. Then we have power generation and storage. Human being have a very good system. We have a stomach, we generate power, right? We eat and we generate power and we store the power. We are capable of storing the power generated inside our body or the energy, right? We consume the food in the morning and then the whole day we keep on working, right? So we must also think about making a robot that has got power and storage capability. Then we have got decision making processor and internal storage. We have a brain, so the robot must also have a brain. And we have internal storage, we have memory in the same way the computer must also have the memory or the robot must also have the memory. Then sense organs for inputs. I told you we have so many sense organs. Although we categorize only 5 or 6 sense organs, but truly speaking, we have a large amount of sense organs. Okay, or sensors rather, basically. So sense organs for input, then learning system based on experience. Okay, human being do that. We learn from our experience. So our system, our robot must also learn from the experience. Okay. And here the term machine learning is very popular these days. So what is it all about? The machine learning is all about how a machine will learn from its experience and use it in the future. Okay. So that is one thing. Then we have learning by networking. We also do that. You have come here. Why? Because you have come to do network and you want to learn, acquire more knowledge. Okay, you make a phone call or you do Google and all those things. And that is a kind of learning by network. You expand your domain by making networks. Then great synchronization between senses, brain and motion. Like human being have very good coordination between brain, senses and motion. In the same way, the robot must also have all the capabilities similar to human. Then unconscious operation going in background. For example, I told you I am already generating energy from the food consumed. Okay, and it is not known to me. I am talking still, my body is working. So in the same way here also, unconscious operation going in background, generating power, coordinating nervous system, updating knowledge. Okay, then robot grew as machines with feedback. This is the evolution of robots. Okay, so machines with feedback, smart machines, then intelligent machines that compete with humans in all respect. Okay, so this is a comparison between human and robot. You can see on different points like coordination, dexterity, then information integration, adaptivity, stable performance, scalability, sterilization, accuracy, space occupation, exposure, and specialty. Okay. So if you go through it, you will find the human and robot. Robot can have great precision. I told you about the firing of bullet. You cannot see the firing of bullet in real time. Okay, but if you have a robot which is equipped with very good high resolution cameras, it can. Okay. So next is dexterity. Dexterity means the skill. So here humans have very high within sensory range. That means if we can sense something or something we can touch, so we will be very quick in responding. We are very skillful in using our resources. Of course, within the limits. I cannot hold a burning piece of coal. Okay, but a robot can do that, right? But if you make a decision like whether I will touch it or not, your system will say no, don't touch. Okay. Then come to the second one, information integration. So here, high capacity on high level and easy to overload on low level. You know, if you make a machine, for example, if you have a pen drive, it has a limit. You cannot load anything more than what is the limit. But as human beings, suppose you read 5 chapters, you can read the sixth also. There is no limit. Okay, there is no limit. You will not forget, and you cannot refuse that. No, I will not listen to your story. You can listen. So as human beings, we have a very easy to overload on low level, right? Of course, I cannot remember a very large amount of data or information, but I can retain. Okay. Then coming on to adaptivity, human beings are very adaptive, whereas robots they depend on design, but are not limited. Okay, robots are also adaptive, right? Then stable performance. So human beings degrade, we get tired. Okay, we are not machines, so we get tired. Unlike human beings, the robots are machine, they don't get tired as long as you have got the power supply or other provisions, right? Then scalability. We are biologically limited, but can increase the number of robots. Human being cannot increase produce a large amount of humans at the same time. But if you have robots, you can reproduce, okay, recreate, and scale the amount. Next, sterilization is acceptable. Okay, sterilization basically means that you can restrict yourself, isolate yourself. Right. Then coming to accuracy, it is biologically limited. Okay, human beings have a limited accuracy. You cannot see something that is far away, right? Like if you have a camera, you can zoom and see what is located on the hilltop. But as human being, I can try to zoom my eyes, but I cannot see that, right? So that is about accuracy. Then space occupation, generally given, it's a fixed body. Human beings generally have an average fixed body, whereas in case of robot, it depends. So it depends on what is the availability of space and how you are going to use it. You can make a tiny robot, you can make a big robot, and things like that. Then exposure. Human beings, we cannot get exposed to radiation or infection, other things. Okay. Whereas if you have a robot, there is no question of getting exposed or radiated like that. Then speciality, it is generic. We can do n number of things. You cannot imagine what we can do. Here, specialized. To make a robot for a particular thing, it will generally do that only. Okay. Now, this is a very common terminology. You might be aware of this very popular character. Okay. I'll not read out all of them, but I'll just tell about this. If you go through, let us just have a look at it. See, a machine repeatedly. This is the term here, and it is pre-designed motion. Okay. If you have a machine, it will do the same thing again and again. Then computer is general purpose. Okay, you cannot use a computer directly to make a robot. Then robot is a mechanical or virtual artificial agent. Okay, carrying out physical activities, complex tasks. It is intelligent and is able to do much more than a machine. Okay, so I told you machine, then we have got robot. Robots are much more equipped than a machine. They are intelligent. They have got many capabilities, what we discussed earlier. Then a robot is automatic and is able to perform activities on its own without the aid of human. Okay. If you think of normal machine, you have to give the input, then only it will respond. Okay, like I told you about this soap dispenser, you have to give an input, then only it will give you an output. Okay. Then what is the important thing here? The term is smart, then intelligence. Okay. And in some fictional work, the difference between a robot and android is only their appearance. We'll just talk about a term humanoid and android. Although android is more related to the phone that we use, but android basically comes from the actual name android. The term means human beings, sorry, not robots which resemble human. These days we use humanoid, a better term for that, but android was the prior term. Then, artificial intelligence is often used to describe machines that mimic cognitive functions. Cognitive means intelligent functions related to human brain. Okay. That humans associate with human mind, such as learning and problem solving. Okay. And finally, we'll talk about this picture now. So, what the picture says, it's about Doraemon. Okay. And in 1969, it became a very popular figure among the masses. Earlier, people were not aware of robots. Only scientists and engineers knew what a robot is. But then, with the advent of this Doraemon, people also came to know what is a robot. And what is it? You can see, appeared in magazines published in Japan. Doraemon is a fictitious cat robot. Okay, who belongs to the 22nd century and has an infinite pocket full of gadgets. Okay, now you can think your pocket is also full of gadgets. Most of you must be having at least one or two gadgets in your pocket. Okay, and pocket full of gadgets from the future. Okay, and remember it's 1969, and if you see the older versions, they will talk about things like camera. They will talk about things like taking pictures, printing, and generating 3D printouts like that. Okay, what is special about this robot is his creative, emotional, good at solving problems, can talk, and has more brain than his best human friend Ruby. Okay, actually, it is a robot owned by a person, and the whole story is that this robot is more intelligent than the owner. Okay, he solves the problem what the owner is not in. Now, this is about the evolution of the robot. You can see we begin with only having mechanical movement. You can see the first one you can see is more about mechanical movement. Okay, the movement of the leg, which were basically actuators and motor control things. Then gradually came the upper part. You can see the upper part actually here also the upper part can control has the controller or the computer, let us say, for the robot. Now this portion started increasing. Okay, computer had vision now, although it was a very poor quality vision, maybe some ultrasonic vision to sense the distance, not to see the pictures, right? Like we have cameras here. Today, robots can see the pictures and interpret. But earlier, it was not about taking pictures. It was about measuring distance from the obstacle. Okay, like that. Then, gradually, we'll see that lower portion also improves. The arms are introduced. Okay, and then you can see the processor, the controlling unit also becomes smaller. Like mobile phones become small. Here also the central processor becomes smaller. And you can see till now the vision part is still missing. Vision basically was still measuring the distance from the optical or next. If you see the 1997 version, okay, here you can see a head is installed, was somewhere in the backpack, okay, and it is more or less now resembling human being, okay, equipped with certain wearing gear that it can uh, resemble human being. And gradually you can see with the advent of Asimo was the first, in fact, operative humanoid. Okay, and today we have humanoids which resemble very much similar to human beings. Okay, we'll talk about some of the very popular humanoids today. Okay, now we talk about the humanoids first. So let us just talk about what are the popular humanoids that are available today. Okay, and the research is all about improving the quality of those. So you can see what are humanoids? They are professional service robots. Okay. See, earlier we were making robot for just doing research or using it in industry. But now what robots are being used to is to work as human being in industry. Okay. They work as professionals in the industry. So humanoids basically are professional service robots. Okay. Then built for interaction with human tools as customer service like inspection and maintenance, and they have skin. See the point here, they have skin, they have eyes, they can talk, and they can walk like human and express a wide range of emotions. Right? These things were not there in the earlier robots, but now in the 20s, we are having robots which are very much resembling humans and they are ready to replace us. You see the first one, popular, Nadine, actually it's the name of a Japanese professor. And this robot you can see, this resembles the same professor. Actually, it is a replica of the same professor. Okay. And it has a body which more or less like a human being. Okay. What is the important thing? That it can return greetings, make eye contact, and remember all the past conversations. Okay. Then she is human-like robot with personality, mood, and emotions. Right? She has 3D depth cameras. Okay. Like we can sense what is inside something. Like if you see a picture, it is a two-dimensional picture in general. Now, if you want to know what is the depth, what is the gap between two objects, you need to have a 3D depth image. So, in the same way, she has 3D depth cameras, microphone, and a webcam to gather visual and audio input, right? And it actually says this robot is working at AIA Singapore, an insurance company, as a receptionist. Okay. Now, moving ahead, this is Gemini DK. Actually, this is also made by the person DK, and it resembles the same person. When these two persons, the actual and the humanoid, they sit together, it's very difficult to distinguish between. Okay, this robot is realistic twin of Henry Scar. Okay, and of University of Aalborg in collaboration with a private Japanese firm in Osaka University. It has been made by these three team of these three groups. It is the latest iteration of Gemini series of ultra realistic androids. Okay, it's very much resembles the actual bird. It took 9 months to craft the Gemini D. Okay, and this bot is very realistic as people tend to be mistaken for the person designed to look alike. Okay, so when the robot and the actual person they sit together, it's very difficult to distinguish. Then this is Junko Kichira. Okay, and it is very realistic Android robot created by Toshiba, right? And Junko works full time in a tourist information center in Tokyo and it was able to respond with the scripted preset speech, but in 2017, it gained speech also. Earlier, it was like something were recorded, like in the railway station, you will always listen some announcements are done. Okay, so those are actually pre-recorded announcements. They make a combination that this train. It was the picture till 2017, but later on, she was granted speech also. So now she can talk. Like you have Alexa and Google, all those things. So recognition capabilities and can respond to tourist questions. Okay. Then Yuko stands 5 feet 5 inch tall, resembles a 26-year-old Japanese woman. I told you humanoids are made to resemble human. Then this is Zia Zia. Okay, this is the Chinese first humanoid robot. And this Chinese humanoid robot puts on a charming, sunlight, realistic and alluring appearance. Okay, she has a very realistic and alluring appearance. This is astounding beauty, can hold normal conversation with person. Okay, with with a microbial face expression. Okay, so what has been done in this is that when she will speak or when she will express, you can feel that it's like a human being. So she may show you anger, you will see it in her face. Like okay. Then another important thing is that she does that with the help of speech generation algorithm and facial recognition technology. Remember, these are terms, these are research topics which have evolved over the period of time, and people have researched in it, and these are the output of those research. Okay. Cloud technology controls the entire action, right? Then it is not that you specifically program it and put everything inside it. It's not like that. It's cloud technology. That means it is not that she will respond at only one place or only on only one topic. Okay, you can keep on upgrading it, right? Then GIA has such realistic expression as that the specific expression was given to her eyes. Okay, so this is the important thing that when the Chinese program this designed this robot, they put much of stress on the eye so that she can catch different gestures. Okay. Of course, when I'm making the eye, it must be some good cameras and some other things are there. We'll talk about that. Different gestures, emotions, behaviors, and so on. Okay. Like if you have a real-time receptionist, so she understands that the person in front is angry, so she has to respond in that way. Okay. If the person in front of her is maybe very, very disturbed, so she has to console and then inform. So these things are incorporated in this GRER humanoid. And this is Sophia. This is the most popular one, and you must be aware of the fact that this Sophia is today also it's one of the most popular. Am I audible properly?
Yes.
So it is most advanced humanoid. It was launched in 2016. One of a kind and her interaction with people. Sorry. Now what when she was launched, she was actually put on a BBC program and she was interviewed. The anchor was asking questions and she was responding. Okay, and that particular conversation became so popular and made her so popular that people accepted. And you may be knowing that she was offered citizenship of some Arabian country. Okay, Dubai. So one of a kind and her interaction with people look like Audrey Hepburn. Sorry, Hepburn. Okay, this is a person actually a famous Hollywood actress, and actually it's not the exact copy of that. It is the advanced copy of that. When that actress will become a little older, she will look like. Okay, it was assumed like. Sophia is the world's first robot citizen. Okay, and first robot innovation ambassador for United Nations Development Program. Okay, the purpose of creating Sophia was to make a robot capable of gaining social skills. Right? Sophia has been embedded with neural network, artificial intelligence to recognize human faces, understand their gestures and emotions. I told you earlier. She can also interact with different people and also respond appropriately. Okay. So this is somewhat similar to what I told you about the earlier one, the area. In case of response, they are supported. Now the next one is this Asimo. Okay. Asimo is more popular and became very popular because of its acrobatic actions. Actually, Asimo can dance very well. That's the most important feature here. So Asimo or advanced step in innovation mobility is actually a short form. Advanced step in innovation mobility. It's a humanoid robot created for search and rescue mission. Okay, and you can see it's not resembling an actual human, but it resembles a human which is equipped with some protective gears. So it can go and detect some bomb or something like that. Okay, it can recognize moving objects, postures, gestures, and surrounding environment as well as sounds and faces, allowing it to interact with humans. Okay, But remember, it is not made in the form of a human being like the earlier ones. Asimo has two camera eyes in the head which capture visual information that detects movement of multiple objects and determine distance and direction. Okay. Asimo can differentiate between voice and other sound that enable it to recognize its companion. It's like you can participate in a group discussion and identify who is speaking. Right. This is figure one. This is one of the latest edition. Okay. Actually, figure one, not much is known about it because they have still not released the entire blueprint of this. So this AI humanoid robot, figure 101, assists people at work as an all-round handy helper. Okay. It has all the features including all the earlier ones. And you can see it has a height of 5 foot 6 inch, 60 kg weight, and it has got a speed, and you can see all the parameters are there. So now suppose you have this figure 01. So what you have to equip it, you have to design it, you have to make up it. Okay, then you can put it as a male, you can put it as a female, you can put it at different places depending on the requirement. Okay, so it has not been given the human look, but it is up to the buyer. If you buy it, you can modify it accordingly. Okay, and this is Emeka. Emeka is world's most advanced, most realistic humanoid. Okay, this is you can see it's a human being again. Created by Engineered Art in 2021. Emeka's first video was released publicly in December and received a lot of attention on Twitter and TikTok. Okay, sometimes you will see like when if you go to Indian Railway, they have got chatbots. Okay, those chatbots come and they can assist you, can type something, it's chatting. Now, when this Emeka was launched, it's called more of responding. Okay, so if you put a Twitter comment, so it can put a reply. You can identify and make a like or make a comment on it. Right. Emeka employs embedded microchips, binocular eye, mounted cameras, chest camera, facial recognition software to interact with public. GPT-3 or human telepresence can also control interacts. Okay, so in fact, this you are aware of the present replacement, the GPC. Okay, GP chat. Okay, so it is also coming from the same company. Keep it in mind. Now, its artificial limbs, ligaments, and sensory array are all made with cutting-edge technology. Okay, so unlike earlier, the robots used to move like this, or slow. Stepper motors were there, but now these robots they have very free movement that resembles more or less like human. And this is the Indian version. This has also become very popular. You might have seen in the Ashta these days they are showing a AI host. He has been named as Sanu. He is written somewhere. Okay. So the newsreader has been replaced. Maybe if you are watching AI in the Ashtak in the evening, they have a program in which she actually reads out the news. She gives the expressions, and you will feel as if actual person is presenting the program. Okay. And it is being copied by almost all the other broadcasting companies. BBC has got its own anchor line. Okay. So this is the Indian version, Indian effect to try to use a humanoid for public broadcast. Now we'll come back to the things we are here to discuss. We'll talk about basic elements of the robots now. So we have got mechanical hardware platform, which generally is a wheeled platform. Arms are there, then sensors, sense and detect objects. Then we have got motors, move with programmed motion. We have got driving mechanism, which include gears, chains, pulleys, and belts. So if you want to make a robot, see, suppose I want to make a robot, I need to think about all these things: mechanical hardware, sensors, motors, driving mechanisms, power supplies. Then electronic controls, I must have digital embedded circuits to control those motors according to the requirements. Then I need microcontroller systems, intelligent programmable electronic kits. Okay. Then I need language because when you go for the kits which are programmable, you need to have some languages to control programming. You need some languages, maybe visual programming languages are used. Then you need servos adjust until they match the signal. Okay. So basically servos are kind of feedback systems. Okay. So suppose our eyes are very much interactive. Suppose I focus torch on my eye will the pupil will become very small. Okay, so that I can restrict the amount of light going into my. In the same way, we have got servo control, we can adjust to the environment. Then we have got pneumatic. Pneumatic means we are using some kind of fluid mechanics to sense the things or transmit the signals. Pneumatic for actuating purposes. You know, all the cars they have got power brake. So have you imagined what is the meaning of powered brake? There is a hydraulic brake. When you push the brake, it is not that you are mechanically pulling the brake with some wire or cable or some rod. When you apply the brake, fluid is there inside the hollow tube, and that fluid actually applies the. So we use the term pneumatics for fluid-based control systems. Then we have got driving high current loads from logic controllers. You may be aware that most of the logic circuits they work with very low power. Okay, and they generate maybe a 5 volt or 3.3 volt DC. So if you have to drive a big motor with that logic controller, you need to have something in between that will take care of all that. So we need driving high current loads from logic controller circuits are needed. We need maybe sometimes we use solenoids or some other relays and other things for that. Okay. Then this is the key component of a robot. You can see there are three diagrams. In fact, you can see the first diagram. Let's talk of A. If you see A, we have got power conversion unit. We have sensors, controllers, actuators, user interface to give the input, and then we have got a manipulator linkage connected to the base. Okay. So, for example, if you just extend your hand to shake with a robot, the robot must know that he has to come forward, right? So this will come from the controller given to the manipulator linker, and the base will have some wheel or some other thing that will take it closer to the person. Okay. In the same way, if you see the lower diagram, you'll see there are objects, object 1 and 2, and the humanoid. Okay. So what is intended here? There is a control system in the head. Okay. And which object is to be selected? It is to be decided. Right. It's not that oh, I will just randomly go and touch. No. I have to take a decision which one is being asked to be touched. Okay. Now come to the diagram B. If you see the B diagram, you'll see there is an input. Actually, it's indicating stimulation, a stimulation from the environment that the input will give, then action for environment. So this is my input side and this is my output side. If you look at it, the first input side, the signal goes to perception module. Like when we touch something, we feel, okay, this is a soft thing, okay, or it is a hard thing. Suppose I have to knock it, so I feel, okay, it's soft. Hard. So we have got a perception module. Then we have got an action decision module. So what is taken here goes to the episodic memory module. Like when we touch something, we remember, okay, I had touched something like this. It was a smooth, maybe the board on the whiteboard on the class. So it's something related to episodic memory module where we take it back to the memory in our system and then come back. Okay, this is that. Similarly, you can see there is a motor module that gives the output, and in the lower side, you can see there is a system control module. Sometimes you have to take a decision, so that is the evolution unit. Okay, evaluation unit. So we have got a system control module which has got an evaluation unit, and it takes the whole decision. All these things are networked. You can see all here in different bidirectional or unidirectional way. Similarly, come to the third diagram, C. In the C, you will see that we have got a basic system and this is the extended system. Okay, extended system includes the basic system. So here, what we are trying to indicate is that there is a habitual behavior by the basic system and goal-directed behavior by the extended system. Okay, like human beings, if you are simply moving on the road, it's good. But if you have a target that I have to chase a particular thing, okay, then I have to decide, no, I have to keep on increasing my speed until I reach the target or or I'm able to grab the moving object, right? Now coming to the robotic vision market, I told you my presentation is mainly on robotic vision because we'll just see why. The robotic vision market actually tells you that there are different domains here. The first is the component domain. Okay, if you think about robotic vision, component domain includes cameras, smart cameras. You know the difference between camera and smart camera, all of you know. Then we have got computer, then come to technology. We have 2D and 3D laser, structured light, stereo vision. These are different technologies that are prevalent. Then we have applications which include welding, painting, things like that. Then industry, electrical, electronics, and automotive industry. You know, automotive industry is driving force today. Okay, because it has got a huge amount of investment. The automobiles, you see, automobile industry is investing a lot of money in automation of vehicles. So we'll just talk about that quickly. And then geography. Okay. Now coming to this, there's a factor, there's a figure in fact. It says that the robotic vision market stood at US dollar 25404 million in 2022, and it is expected to advance at a compound annual CAGR. You may be aware of the term CAGR, compound annual growth rate of 9.5. This is much more than the average GDP of the whole universe, right? So during 2022 to 30, it's expected to reach 497. Okay, it's a very large amount, a billion by 2030. Driving factors: demand, safety. What are the driving factors for this investment? Because people or the industry demand safety, reliability, accuracy, okay, efficiency, and ease of implementation. And finally, the penetration, that it will come to the public usage. Like mobile phones, they are penetrated into the mass. In the same way, we want that computer vision, including in automobile industry or different other places, will become penetrated into the masses. Okay, and this is what robotic vision market is continued. You can see when I talk of this robot, you see this is a very simple old type of robot, but what is inside the head part? Okay, we generally keep the camera on top. This is the common perception that if I have to take an image, like he's taking an image, he raises his hand. He can take it from here on. So if you look at the helmet part, the upper head part, you see what is inside the head. See, gyroscope. Why gyroscope is needed? Because see, human beings are very intelligent. We keep our head in different angles, and it is all known to us. Okay, suppose we are having a good look, you can do like this. Okay, if you are walking, we keep it like this. Okay, so there is a gyroscope. Gyroscope will help you know your actual position. Okay, then we have got microphones. You receive the sound signals like our ears. Here, the microphone resembles the ear. Our ears are microphones. Okay, we have a stereo microphone, two ears. Okay, unlike this microphone, which is right now, although there are two elements here also, but this is mono microphone. Right? Humans have stereo microphone and video signal. Video signal means my eyes. So I have again a stereo vision. Okay, you must have studied stereo vision and mono vision. If I close my eye and I walk through this room, I may not be very comfortable. Why? Because I will not be able to know the depth. Okay, but when I have two eyes, I know the depth and I can walk very confidently. Right? Then you see there is a motor. Of course, the motor is there to keep the head move in different directions. Right? Then we have got motors at different type of motors. One motor may be for rotating, one motor may be for lifting the head, like we do like this sometimes. See, if you look at my head, sometimes I do like this, sometimes I bend, then I rotate, sometimes I look like that. So we have more than one motor. You can see one, two, and three motors. So this will give you the three-dimensional availability. You can look at any angle. Then we have got the microphones. I told you stereo microphones. Then camera is there in the center. Okay. Now you also know the significance of multiple cameras. Earlier in the mobile phones, there used to be only one camera. Okay. Can you answer my question? It's a very simple question. Why we have more than one camera in the mobile phone? The camera there is only one lens. You see, the camera is holding someone that DSLR. It has got only one lens, isn't it? So why it is so that in my mobile the camera is having two or three or even four, five cameras? Who will tell me an answer? बताइए. Are you getting my question? My point is that this camera, see this camera, I'm sorry, this camera is a DSLR, you know DSLR, it has only one lens. Okay? So why in my mobile there are two, three or four cameras? Who will tell me? All of you are having mobiles having more than one camera. So why you have that? Okay, again I will ask the same question. So you can see that if I try to think about the robotic vision, it's not just about putting a camera. Okay, like human beings, we move our eyes, we move our head. Here also we want to equip our robot with that kind of a vision. So now when we move ahead, my answer, the question will get answered if you go through the next slides. So our processing actually what we see, the vision, it includes two parts. One is the image processing part and the other is computer vision. Okay, so what is image processing? Image processing basically means manipulate image data, generate another image. Okay, so I told you when you take a picture, you may edit it, you may brighten it, or you may remove the background or other things. That is image processing. And when you do that, you get an output that is an image also. Okay, that is an image only. Maybe it may sound or may appear very good to you, but another person may say it's not a good image. Okay, Now, the second thing is computer vision. What is computer vision? And my answer to the question why we have more than one camera is also means answered. Computer vision basically means process image data. Okay, it's about processing the image data, not the image again, and generate symbolic data. Okay, so what is the meaning of this? If you look at this image actually tells a story. Okay, it shows that there must have been a high elevated platform or railway station from where the engine, you can see the old engine, this is actually engine, it has fallen down. So if you show me this image as a person, I will tell you the story. It seems as if there must have been a high elevated platform or railway station from where the engine has fallen down. This is from my experience. Okay. This is from my experience. I will just see, okay, this must have happened sometime in history and it appears to be an old engine. So the whole thing is written here. The goal of computer vision is to write computer program that interpret images. I have interpreted this image. Someone else can interpret it in a different way. Okay. Someone else can say that this must have been kept in a showcase and has fallen down. The toy train. Okay, this may be also one interpretation. So interpretation means when computer vision basically tells you how you can interpret the image, what information you can extract from the image. Okay, then can computer match human vision? So truly speaking, yes, but no also. So see, the answer is yes and no, but mostly no. Computer vision cannot match human vision. Okay, because human vision comes with our brains and we are more intelligent, we are very much experienced. So what is the answer? Humans are much better at hard things. Okay, computers can be better at easy things. Are you getting my point? So human brains, suppose I show you 10 type of apple and give you a feedback that this is red, this is sweet, and like that. If you get the 11th one, you can tell, but a computer may not do that perfect. Okay, because human being we get so many things in nature, different type of things come to us and we never have seen the earlier one. If you see an apple, you might not have seen that apple earlier. Okay, a red apple you might have seen, but if you get a new apple, it's always new, it's always different from the earlier one. Okay, so here is the answer, again the answer that humans are better at hard things. Okay, and computers are better at easy things. It is programmed. If it has got the data, it can tell you the answer. Now, computer vision basically means reconstruction. So, recover 3D information from data, like I did in the case of the earlier picture. And recognition, detect and identify objects. I did that. It was engine and platform or railway station. And understand what is happening in the sea. Are you getting it? I can go back and tell you. See, this scene is a picture for a person. Okay, if you show it a computer, it may not tell you. The computer may not tell you that it is an engine. It might have fallen down and things like that. So uh, I reconstructed, then recognized and understood. Okay, so computer vision basically means reconstructing, identifying, and then understanding the message in the image. Now, this is also a very good example. See, this is about human perception or a kind of illusion. Okay, what you can see, some people can see that snakes are rolling in their coil. Okay, although it is a static image. Okay, if you put a lot of attention on anyone, you will find that it is like a snake is rolling or making coils. Okay, can you see that? Maybe two. So if you look at the system overview for computer vision, you will find in case of digital image processing, we capture data, data. Then enhancements are done, feature extraction is done, feature recognition is done, then image recognition. Okay, suppose you take all of you are aware of Google Lens. Okay, your mobile phones you have Google Lens. So what Google Lens says that don't type that I want a object like this. What you do, you open your camera and take the image of the object. For example, if you take the image of this mic, Google will automatically tell you that this is a microphone. It appears to be 9-inch in plane and it appears to be a stereo mic like that. Maybe it can identify the logo or the QR code, something like this also. Okay. So what it does, it captures, then enhances, then feature extraction is done, then feature recognition is done, and finally image recognition is done. Okay, these things have become very popular. Earlier, it used to take time. Okay, suppose you switch on your camera, take an image, it used to take time and then finally tell you an answer. Okay, that this appears to be a mine. But now what has happened, the processing speed has become very fast. The algorithms are long, but the processing speed has become very fast. Okay, now if you look at this image representation, so we have got image capture, the image quality measurements, resolution, color representation, camera calibration, and parallel. We try to parallel with human visual system, right? Now, this is a very good example. All of you are aware of the high security number plates in the vehicle that have been implemented in India also, in our state also, different places. So, what is the purpose of this? That you first take an image, then you separate the items, and ultimately you identify each of the individual details. Okay, this is an example, very good example of optical character recognition. Okay, this is about character. It was a old thing. It dates back to say 15 years. Okay, we had a scanner which to scan and then it produce the output. Okay, then this is also very common thing. All of you are aware. We have got face detection systems. Okay, our cameras have got intelligence. They can detect the faces. All the cameras these days they have it. Okay, but remember, it's not just because of the camera. What is actually happening? The image is taken, it is processed, okay, compared with certain set standards, and then it tells you that okay, this is the face, this is another face. Some faces may not be captured. Okay, sometimes suppose a person is having some acute angle or some other angle, he may not be taken in the face. Okay. Then we have got this one. This is smile detection. Most of the cameras now have smile detection. You don't have to put the shutter button. Okay. Whenever there is a smile, it will automatically take the picture. Sometimes you get a message, eyes closed, blind eyes. Okay. When you take a picture, person may close his eyes. So what the camera will do, it will take care of that. That if the person closes the eye, it will take a picture, but it will wait for the person to open the eye again. Okay. So that is also a technology. Then we have got object recognition in marketplaces. You know, these days, earlier they used to use a barcode. If you go to the supermarket or mall, they will use a barcode or QR code, something like that. Nowadays, you will see they don't do that. They just take the object and take it in front of the camera. Okay. Earlier, they were using a barcode reader, handheld laser operated device, but now they are not doing it. They just take the image, take the object, put it in front of the camera, and it is identified. Now, this is also very prominent story. It was about a terrorist, okay, Afghan terrorist, and she was recognized just because of the iris pattern. Okay, so this iris pattern has also become very popular way of identifying people in the Indian system. Also, we have got the Aadhaar card, which recognizes you on the basis of not only your fingerprints but also on your iris. Okay, and the iris of persons are unique. One person will always have unique iris; it doesn't resemble any other. Um, this is about the fingerprint sensors in the mouse. Okay, different places now. Even if you go to take out money from hotels or some newer type of ATMs, you can just put your finger. You don't have to put any number, any other thing. The finger is, sensor will sense it and maybe it will recognize from a huge amount of data. Aadhaar database is also like that. Then this is about object recognition. Okay, you can see if you take the image like Google Lens, I told you if you take the image, Google Lens story about that image using the net, of course. And this is about how we use the computer vision in sports for identifying different type of cases. We have got a very unique thing that is smart cards. Okay, and I told you that the industry is driven by the computer vision concept. The smart cards or the driverless cars, they will become possible and they have become possible only because of the sensors. We'll just have a very look at it. See, in this picture, you can see there are two parts. There is manufacturer product and consumer product. Okay. If you look at it in the car, we expect to have side looking cameras, rear looking cameras, and forward looking. Okay. And what are these things you can see? We have eye, the chip, then we have vision application, road, vehicle, pedestrian, they have to be identified. Then we have advanced warning system. Okay, suppose this is very common nowadays. You will find that there are parking cameras, and some of the new cars they are equipped. So when you reverse in your car, you will get a message that there is a little gap between the wall and the parking wall and the the boot of the car. We get a message why that is called advanced warning system that you don't have to go back, otherwise you will hit it. Okay, these are actually presently in these cars only, but right gradually with the passage of time, they will come into the cheaper version of the cars also. Okay, this is about robotic games and other things and how the robots are used to do things which human being cannot do directly. Okay, like going to Mars and collecting samples and other things human beings cannot do, but this is possible. And there's a another diagram picture that tells about the interactive entertainment part also, which robotics can be used. Okay. Now we'll talk about the different type of sensors that we are using in the smart robots or the humanoids. We have light sensors, it can be photoresistor, photovoltaic cell, phototubes, phototransistors, charge coupled devices, etc. We have sound sensors like microphone. Okay, we have temperature sensors, many different type of temperature sensors are there. We have contact sensors like capacitive touch. You know, contact sensors are very prominent in the mobile phones. When you touch your screen and expand. Okay, earlier we used to have touch, capacitive touch. Now we don't have to touch. Today we don't touch the screen actually. There's a layer. You can put a screen guard or a tempered glass. So we are not actually touching the elements. We have contact sensors. We have got proximity sensors without any physical contact. Your mobile phone knows. If you approach it, it will know. Okay, it may blink. Sometimes you might have noticed it's the dark. Put your phone and you approach it. It may blink and tell you that I am here. Okay, then a transmitter transmits an electromagnetic radiation to create an electrostatic field, and receiver receives and analyzes the return signal for interpretation. Okay, can use IR, infrared, ultrasonic, or simple light. Okay, then we have got different type of distance sensors. Okay, you can have range sensor, distance sensor, you have precise infrared distance sensors, laser range sensors. Okay, you have encoders who can detect the angle or the rotational aspects. You have got stereo camera. Two cameras placed at to each other can provide depth information using its stereo vision. Like I told you, if you close your eye, you will not be able to distinguish who is sitting behind and who is sitting in front. Okay. Then you have got pressure sensors, and this is very important now. If you make a robot, very humanoid type of robot, the robot must sense that the person who is shaking hand have to apply a little bit of pressure also. Okay. And it has to be proportionate to the person who is the shaking hand with. Right. So pressure sensors are important. Then we have a stretch and bend sensor, pressure sensor. Then we have got tilt sensors. Okay. Remember, all these things are very useful when we talk about the autopilots. You are aware of autopilots, right? When the planes fly, sometimes the pilot do not hold the steering and all those things. They just sit and observe. In that case, everything is controlled by the autopilot. And the autopilot must know what is the angle of the plane, at what angle it is pitching or taking up, what is the tilt of the plane, what is the speed, all those things. So these things are measured in the flying plane, and all the things are controlled by a computer. And the computer takes a decision whether if the tilt is on one side, it has to level it back. Okay, or if it is pitched down, it has to be leveled again. So those things are reality. If you look at different type of sensor, again, we have sensors for navigation and positioning sensors. Okay, we can go for digital magnetic compass, which is also, of course, the most prominent and useful uh, position sensor. And we have got localization. There are different schemes you can use to localize. Like when you move on the train, you can know. Sometimes you will see you can use GPS. Sometimes you can use the cellular network, right? And sometimes if you don't have all those things, you can think about some Wi-Fi or some other thing that can also tell you your position. Okay. Then we have got acceleration sensors, static force, dynamic force. There are different type of things we can measure. We have got a gyro. I told you in the earlier part only. The gyroscope is a very important thing, and it will help you know the or measure the rotation aspect. Okay. Then we have got IMU. IMU is very important. I told you about the autopilot. Autopilots work on the basis of inertial measurement unit. Okay. If you see the autopilot or if you see the plane actually, inertial measurement system is there. And what it does, it has got, just imagine that you have a tube and there is a drop of mercury in it. Okay. So when you move the tube in this direction, the mercury will go this side. If you move it in this direction, if you want to level it, it should remain in the center course. Right. So in the same way, the autopilot also works using the inertial measurement system. Okay. Then you have got voltage and current sensors for different type of things known to you, so I'll not put this here. Then we have got different ways of okay. Image is sufficient. You can see you can have a single unit in which there is a transmitter also and a reflector also. So you transmit the light to the target and it will be reflected back. Like humans also do in the same way. But what is the drawback? See, if you go in dark, you cannot see anything. Why? Suppose you want to see something, you need to have light. Our eyes, they cannot generate light. Remember, we never generate light. That is why we are not able to see in the dark. If you want to see an object in the dark, you must focus light on it, and that light will be reflected to you. So our eyes are only sensors. They are actually sensors. They can only sense the light. They cannot generate the light. So unlike our eyes, here you can see that this detector or this light detector system, it has a transmitter. It will transmit the light and then it will detect. Now this light may not be visual light. Like in the CCTV cameras, you will see they use the IR light. Okay, infrared light. So that is one aspect. Then if you look at the C, this is a different one. Here the transmitter is separate and receiver is separate, right? So if there is an object or target between it, then the interruption will be there and maybe it will be detected that something has interrupted or come in between, right? This is one example in which we are using light and this is called through beam model. Through beam, there's a beam and if you obstruct it, then it will come to know that something is wrong with the okay, now this is another one. See, this is slightly different. It's called detection based on light and this is retroreflective model. Okay, if you see this, here we have transmitter receiver in the same unit. We are transmitting it to the target. Target is certainly not reflecting the exact thing. It is partially reflecting, or rather, only a part of it goes to the reflector, then it is reflected back again going to the target, and then okay, so there are different ways. We study about these things in the optics, physics of light. We study all these things. Then we have got through beam model again. Has been got this detection based on eddy current. Okay, some of you may be aware. You use the induction heater. Most of you must have experienced using induction heater. If you are heating something in a vessel, okay, and you just lift it from the stove, have you noticed that you can feel the vibration? Okay, when you put some, let us say something to be cooked or milk and you are boiling it, and you just take the vessel, lift it, you'll see again heating is lost, no heating. Okay, when you bring it down again, heating will be there. So basically, when we are using the inductive IPS system, it can use inductive proximity sensor. It can use the high frequency magnetic field sensors. Like if you see this diagram, very good diagram, you can see when you have a metallic object, when it is present, the amplitude decreases and frequency also changes. Okay, so there are different ways of detecting. Inductive proximity sensors can be used for non-ferrous metal types, ferromagnetic material also. Okay. So in order to use these sensors, remember these are sensors, but they give the vision to the robot. The robot may use all these things. Okay. You are aware of the metal detectors. They when you go to any maybe official government building, they will detect whether you are carrying any metal with you or not. Okay. There are loops in which you are asked to go through. Okay. So they are using all these concepts. And these things give vision to the system, right? Now this is again the same thing you can see. If you look at it, see the magnetism, strong, weak. You can see the diagram is very good. Just have a look at it, right? Here it is telling about magnetism, detecting distance of general purpose model, detecting distance of aluminum detection model, and typical metal. Okay, so what is the meaning of this? See, if you have an aluminum object absent, it will be like this, then the frequency changes. Okay, this is a way of detecting object, providing vision to the robot. Okay, then there are detection based on contact measurements. Like here you can see this one you can see there is a contact. Okay, so suppose you want to measure the height of person, you might have seen they have a triple leveled roof type of thing or a cardboard, and you just go and they will measure it. If a taller person will go above it, may go down. So that is a kind of contact measurement system. Similarly, you can have Non-contact type of measurement is also there. You can have air push type measuring by spinning the spindle. Spindle means this the thing that can be moved up and down. Okay, like you must be aware of things like screw gauge, where we rotate the spindle and we measure the gap between two things. Okay, or you measure the width of some target. Then this is a comparison based on some types. Okay. So you can see inductive, optical, ultrasonic, laser focus, contact. There are different ways of measuring the distance. And here detectable target, measuring distance accuracy. So this table actually compares which scheme should be used for measuring the distance. Right? This is actually a table I'll just pass this PPT, you can have a look at it. Now, detection based on ultrasonic waves. You can see ultrasonic waves are very interesting because you can use this ultrasonic waves where you cannot use the radio waves. For example, if you want to measure some distance in seawater, you cannot use the radio waves because the radio waves gets absorbed in the saline water. So there you can use ultrasonic measurement. Other thing is that if you have to measure very short distance, you can use ultrasonic detection. Okay, and this detection is undetectable because you cannot see it. If you are using light or infrared, you can visualize it. But if you are using ultrasonic sound, it is not in the range of your human ear, so you may not be able to listen it. It's a kind of covert measurement. Okay. Then we have got different ultrasonic level sensors. Okay, that can be used for transparent object detection, resist to mist and dirt. Okay, complex shaped object detection. We have detection based on camera images. We have discussed a lot about this one. Okay. You can have with a vision sensor, use image captured by camera, you can know the presence, orientation, and accuracy of object. If you take an image, you can know about these things. These sensors differ from image inception systems. Okay. Camera light, controller, and controller contained in a single unit, which makes the unit construction operation simple. Okay. Then, like you have seen the CCTV cameras. Okay, you will see the light source is also integrated in your mobile phones also. Some of the mobile phones, the advanced ones, they have cameras that are equipped with IR sensors. Okay, you must have heard of terms like XMOD sensor. Generally, cameras use it. XMOD, CMOD sensor, other things are there. So those cameras have integrated light source in all. Okay. In addition, due to wide field of view, it's possible. Even target is not consistent. You must have seen that they advertise like this camera or this video camera can capture even in motion. Like if you are sitting in a vehicle, there will be motion, vibration is there. Still, the picture captured by the camera will be static. Most of the cameras today in the mobile they do that. It is called image stabilization. Okay. It just removes the vibration aspect from the taking videos. Then this is about monochrome model of vision sensors. Now in the diagram, if you look at the diagram, see, can you understand what is the meaning of this diagram? Have a look at the diagram. You see the diagram. Are you able to understand it? There are two things. See, in the upper part, see, there is the image. The contrast between white and black spots is identified. Okay, so there's a gap. And then profile difference are identified to determine shape orientation. Okay, profile difference. Similarly, here brightness difference are detected. Right. So one thing is that you are trying to identify the object. You are detecting the object. The other is identifying the object. Okay, human beings also do that. Sometimes you see that a person is coming, then you realize no, he is my friend. So first you detect that a person is coming, then you identify. Right. Here also the same type of thing. This is the color model. In the color model, what we do, when we take a monochrome image, it's simple black and white. But when we have a color image, we break it into different components. Okay. For example, here the identification like target with same shape but different color, dark blue and dark. Okay. So this is a slightly different thing in which we are using a sensor that separates the received light in different components. Maybe cyan, magenta, and uh, yellow. Okay. Or CYM, some combinations are there. Right. Now let us come back to the whole thing. See, to extract, characterize, and interpret objects present in image photograph using camera. Steps to be followed. Capture image of environment using CCD camera. Then light intensity is measured along particular direction, say Y, using electron beam scanner, in which charge accumulation in photo sites is proportional to light intensity. Okay, like the old video camera, they used to work on this concept. Then analog plot of light is digitized and known as analog to digital conversion. Image is stored as an array of pixels. Like we take a when you take a picture, it is stored somewhere in your memory. It is known as frame grabbing. Okay. Right. I'll be a little fast, okay, because I don't have much time. So if you look at this, fourth is the pre-processing of data collected, which actually is done for noise reduction, restoration, and lost information. Okay. So if you see this diagram, see sensing and digitizing image, light, then lighting, then camera, then analog to digital conversion, then frame grabber, and then we send it to the CPU, and finally, what is done? See, we save the this is the processing part of the whole computer vision apple. Finally, it is sent to the interface, then to the robot controller, and the task is executed. For example, I told you if I have to identify when Mr. X is coming, I have to shake hand. So the whole thing is done. First, the computer vision, robot vision has to detect the object, identify the person, and then decide whether I have to shake hand or not. Okay, so that is the task. So once I identify that Mr. X is coming, I have to welcome him or give a speech to him and then shake hand with him. So that is the task based on the robot vision. I'll not talk about the. If these are actually image processing tools, more of mathematics, so I skipped it. Now, if you look at the summary of computer vision, to just summarize, try to summarize, you see, we have an object, the image is acquired, image is processed, okay, then statistical analysis is done, finally the output. Okay, for example, you take a picture, okay, like we do, it is very common scanning the QR codes. Okay, so what we do, we get an object, you open your mobile phone, the object is there, then you take the image, okay. Now you are just taking the image. How the Google or Pay or Phone Pay knows that you have to pay this person? So what happens? Image processing is done. The statistical analysis is done. Who does this statistical analysis? The Google Pay or Phone Pay, they do that. Okay. Then they identify the person and gives you output that this account number, this person is to be paid. Okay. Then this lower diagram you can see there is a sample, illumination, then there is a camera. I told you human eye, we need illumination. In the same way, there is a sample, illumination is needed, then the camera will take the image, the computer will process. So first we have pre-treatment, that is called noise removal, contrast enhancing, then segmentation, then feature extraction, then we finally identify it. Okay. Why it is called QR? Because it is designed in such a manner that you can do all these things very quickly. Unlike identifying the person. Suppose it could have been like this, that you take the person image from the Aadhaar database, you will come to know who is the person and then you pay. It could have taken a lot of time. But when you make the QR code, the person is registered, okay, is having a database with the bank or the company that is taking care of the UPI. So it is very fast. Okay. Now, these are the research opportunities. Suppose we are discussing about this. Karyashala is all about doing modern research, improving the quality of research, and giving research output. So these are some areas in which you can think about doing research. First is human-robot interaction and interfaces. Then robot motion planning and control. Then medical robotics and assistive robots. Novel sensors, actuators, and robot designs. Then robotics and AI, sensing and perception, human augmentation, okay, and robotic manipulations, soft robots. Okay, soft robots basically means robots which can take soft decisions. They can use the artificial intelligence and soft computing tools to take decisions. Then you have got autonomous vehicles. Okay. Then embedded systems for robots and multi-robot systems. These are different domains in which you can do study. And I'll end with showing you uh, I've got two videos that I'll just show you. They're very small videos. First one is about this autonomous car. We have a
Self-driving vehicles can detect obstacles and stop if necessary. With the help of sophisticated technology, vehicles from Navaya, Waymo, and local motors are able to pick up passengers on demand and take them to their desired destination. Autonomous vehicles are also able to recognize traffic lights and road signs at intersections and act accordingly. But how do they actually do all this? Self-driving cars do not require a driver to get from A to B. The technology in and on the vehicle is the driver. The technology includes many sensors, such as lidar sensors, ultrasonic sensors, cameras, and radar sensors. The sensors are located at the front and the rear of the vehicle. The cameras and lidar sensors are also frequently found on the roof. Without them, the vehicle would be virtually blind. LiDAR is a key component in many vehicles. LiDAR works similar to radar. LiDAR, however, does not use radio waves, but many light rays that are reflected by the objects in the surroundings and detected by the LiDAR sensor. In this way, a point cloud is generated from the environment. However, LiDAR does not recognize road signs. Cameras use artificial intelligence to recognize and interpret street signs. Cameras are also used to detect obstacles and are needed for lane keeping. Neither LiDAR nor cameras can handle fog. In this situation, radar is needed for forward collision warning and avoidance. A major disadvantage of radar, however, is that the objects must be large enough to be detected. Pedestrians or cyclists may therefore not be recognized by radar. The exact position of the vehicle is determined by GPS and highly accurate digital maps. Digital maps contain a lot of information, including information such as intersection signs and speed limits. Since GPS cannot always be guaranteed, for example in tunnels and street canyons, odometry is also necessary. For example, the wheel diameter and the wheel speed can be used to estimate the future position of the vehicle. All data from sensors are then combined and processed in one or more processors. NVIDIA, AMD, and other manufacturers offer such chips for autonomous driving.
I think you had a good look, and you can see how the automobile industry is taking advantage of the computer vision, code vision, and using the robotic vision. You can think about implementing truly driverless cars. Okay, and of course, it's not all about robotic vision. You have to take advantage of machine learning and other different things and aspects are there. So my focus on this whole presentation was that how you can do research in the area of robotic vision. Okay, there is a lot of opportunity and then have explored all those things. You can choose any one particular area and you can think about going into depth of it. Okay. So finally, these are some of the references. So if you have any questions related to the presentation, you can ask me. Any questions? Any questions? If you have, or anyone can answer now my question: why the mobile cameras have, of course, one. Why the mobile cameras have two cameras? Why? I put a very simple question that camera that DSLR is having only one lens. So why the mobile cameras have more than one camera? They are having two or three lenses, even four lenses. Who will give me the answer? Definite appreciation for that person. बताओ कोई जरूरत. The answer was given during the presentation also after that question. See, with a single lens, okay, with a single lens, it's a yeah. Well, that is not the exact answer. Any other thing? Good quality. Any other thing? Actually, if you take two pictures, okay, both the pictures will be separate. One camera, second camera. Okay. Wide range. Okay. That is also somehow somewhat true. Any other thing? See, actually, the earlier cameras we used to have, we used to put our eyes and see the actual object. Okay. And it used to be filmed on the photographic plate. Unlike that, what we are doing now, we are taking picture. Okay, we are processing, we are doing image processing, right? And it aids us, it helps us to take a better picture. Okay, so if you have only one camera, your image processing would have taken more time. If you have more number of cameras, the image processing will take less time. Okay, that is one answer. Other answers are also there. Any other answers? Yes, tell us, Sarva.
Actually, how to interface robotics with IoT. That in the simple language.
Okay, although I did not give a presentation on that, but I can answer your question. See, if you make a robot, basically the robot is autonomous, okay, and it is supposed to work autonomously, okay. But these days we have to give the robot the capability, like we have mobile phones, we become connected with the world, okay. So we have to give the robot also a connectivity like this, okay. So when you have to give a connectivity like this, you have to have something that will connect the robot with the network or the cloud, okay, or the server, some remotely located server, or some things which it is supposed to control, right? So that requires the infrastructure based connectivity. If you want a robot to become connected or use IoT, you have to provide it a capability similar to this. So you have to interface a connecting device with the robot. Truly speaking, you have to interface the mobile phone with the robot, right?
Yeah, right. And I think you talked about image processing.
Yeah, image processing and computer vision.
Yeah, so recently I have submitted one project DSP sponsored तो उसका नाम दिया है गौ सेवा इमेज प्रोसेसिंग बेस्ड द काउ केयर टेकर तो उसमें सिंपल मैं बताना चाहूंगा जैसे यूरिन कलेक्शन करने के लिए हाउ टू कलेक्ट द यूरिन in real time and whether it is feasible or not. So we thought about the image processing. तो क्या ऐसा है जैसे गाय दूध खिलाए तो इमेज प्रोसेसिंग के थ्रू डिटेक्ट कर ले कि हाँ ये फ्रूट खिला रहे तो ऑब्वियसली यूरिन के लिए तो गेटिंग पॉइंट ना तो उसको कैन वी डिटेक्ट इट थ्रू द इमेज प्रोसेसिंग.
Yes, it is possible. See, we try to make a humanoid, and humanoid is supposed to imitate a human being. Okay, a humanoid is supposed to imitate a human being, so obviously it has the capability of doing this. Okay, the only thing is that it has to observe the target. Okay, that will be possible with the help of computer vision. It must have the intelligence to interpret based on the experience. So it must have some learning skills. Okay.
Yeah, but the problem is there.
Yeah.
You how to detect how is about the urine.
See, it will be based on the experience. So you have to train your system. You design a system, take the images, okay, and in real time you learn from that. Okay. Initially, you have to train your system. Once your system is trained, because the behavior is common in general. So once your system is trained, you can use that to collect whatever samples you. It's not very difficult because there are automatic robots which take out the milk. Okay. So if the robots can use that system to take out milk, they can also do to collect urine and other samples. Right. The only thing is that you have to train, and with training, the system will become advanced and more accurate. Okay, so I think I can conclude now. Thank you for your patience listening. Thank you very much.
Thank you, sir. Now, I want to invite Dr. Vijay Kumar Dalla sir for presenting a token of gratitude to our esteemed speaker, Prashant sir.
So, Jayakumar Delas sir and Prashant sir both are co-coordinators of this event. Sir, it should be sorry, sir.
What about?
कभी हो गया ना उनका नहीं है ये स्टॉप हो तो गया लेकिन मिलेगा मैं चुनने का काम से
He has great exposure in the field of robotics and he is a student of his yesterday we he was the invited lecture, however through the online mode. So he is the product of Professor H.K. Saha. And when the sir was working as the assistant professor in BIT Ranchi, so generally हम कहीं पे इंटरव्यू के लिए खुद फॉर्म अप्लाई करते हैं, इंटरव्यू के लिए कॉल किया जाता है, फिर उसके बाद हमें मौका मिलता है. तो सर का खासियत यह है कि डायरेक्टर सर ISM धनबाद के डायरेक्टर सर इनके इंस्टीट्यूट में इनके लैब में विजिट करने के लिए गए थे. थैंक यू. या
चलो करना नहीं हम सब बदल रहे हैं
आप बोले 30 लोग हैं. अगर
मतलब भर भी से मजा आएगा तब तो call your friends, call whosoever are there. Next time now, 1 hour at least. Not hungry, no? Very good. You have to build little energy to hear robotics. So robotics is something that does some job, no? मशीन काम करेगा आदमी सोएगा बोलने कब से पर
ना अगला कर दे. हाँ डुप्लीकेट कर दो सारी बात कर दो. बहुत सही है क्या?
Hey, David. Yes, sir. नहीं So, I'm Arun, not Arun Kumar Uday. I am Arun Dayal Uday. हाँ तीन नाम है. तीन नाम है. लास्ट वाला मेरा है. Just like South, basically South So last one of Uday, you can call me Uday. It is UDAI. So little difficult to pronunciate that. So anyways, I did my PhD in 1910 under Professor Shah in Department of Mechanical IIT Delhi. 2010 to 15 I was there. I was working as research scholar in UARC project. So quite number of slides that I'll show, experiments mostly, not 100% slides, is from their lab, and few of that is from VIT Mesra, where I was teacher also there. Okay, as assistant professor, I was in mechanical VIT Mesra also. So there also I was in robotics lab. So I've been teaching robotics since last, I think now 14, 15 years. Okay, 15 years approximately. Okay, so and into robotics almost 20 years. तो खुदा हूँ मैं, ठीक है, बाल शायद उतना काला नहीं है. So anyway, don't go by that. So yes, so you have to be with it. Listen carefully. You have to be with it because each and everything that I'm going to start from the beginning, no, it counts. I am audible enough. इसमें synthetic लगता है इसमें. Class is quite peaceful. It's audible enough. So I'll be talking about cobots. Why cobots? Cobots mostly अभी बात चर्चा उसी में है ना. ज्यादातर robotics is already age old. I don't know why it is still latest. जो लास्ट पेटेंट फाइल हुआ था, I'll show you, it was in something around 1950. So it is 1950, as good as steam engine, IC engine and all. And robotics also was around that time, it was there. Still it is new to us, not new to world. Okay, so we have to come up. We have been lagging because the type of interdisciplinary nature it demands, right? जिस तरह का इसके लिए ट्रीटमेंट चाहिए ना, वो एजुकेशन सिस्टम में है ही नहीं. मैं ऐसा कैसे बना? Why I am able to do it? Why many others who are doing it? So you have to inculcate that habit of learning. मैं मैकेनिकल का हूँ. The day we join a branch ना, आज से मैं मैकेनिकल का हूँ, तो मैं सिर्फ बिजली के खंभे नहीं देखूंगा. ट्रेन से आऊंगा, इंजन छोड़ के इंजन ही देखेंगे, खंभा नहीं देखेंगे. ठीक है, you specialize, no? You stop that specialization and you get into robotics. I don't know how many of you are actually doing robotics or have some passion to do robotics. How many of you? Which branch? Which anyone? रोबोटिक्स क्लब से हो, कहां से हो? कहीं से हो तो दिक्कत है, कहीं से नहीं होना. So you have to begin with your basic nature. Now how we start education is we were scientists first of all. ना हम लोग पहले साइंटिस्ट थे ना, स्कूल डेज में वी वर साइंटिस्ट बेटर, है ना. फिजिक्स पढ़ते थे, केमिस्ट्री मैथ सब पढ़ते थे. द डे वी गॉट इनटू इंटरमीडिएट, थोड़ा साइंस पर स्पेशलाइज हो गया. बायो आज से नहीं पढ़ेंगे, मैथ साइंस. फिर और आगे बढ़े, देन वी बिकेम इंजीनियर. फर्स्ट ईयर वाज ऑलमोस्ट कॉमन. We talked about engineering and then we talked about mechanical, electrical, specialized. Okay, so we left that thing and we have to come back to that, right? So that is what is required in robotics. You have to be with uh, all over the branches. No, it is such a huge interconnection between different branches that uh, it is not possible to even talk with an engineer who is doing robotics. Even to talk with an engineer who is doing robotics, you need some basic prerequisite to discuss with them. Few bit of electronics, sometimes mostly programming, okay, and mostly mechanical where most of the robots fail. Okay, so most of the robots they fail due to mechanical. They cannot build due to electrical motors. India is not making a motor. We are into EVs. We want to make EV, and you see we have elevated the price of IC engines also. Just 2 years back when EV was not there, scooters were along 70,000 में मिलता था. The day EV get in, EV में क्या होता है? खाली everything is Chinese. Your BLDC motor driver, some controller, accelerator. That's it. And it is velocity controlled. That too human in a loop. It is not automatically controlled. Right. So everything imported. Cost of EV came up like 1 lakh. Okay, scooters, जो IC engine scooters, which has much more number of parts, we were mature in making that. We were selling it in 70,000. Now that also has elevated and came up to 1 lakh. Right, that is the reason. So EV has elevated the price. We were expecting EV will bring down the price. It will bring in a competition. So that is what is the problem, right? We don't make anything. We don't make actuators. We somehow started making IC engines well, but we again failed because of this mechatronic nature of EVs. Same with robotics. Same with robotics. That interdisciplinary thing is totally missing. The way we are brought up, the way we are trained, the way we are doing robots. So cobots is not much different. It is similar to robots. I'm talking about cobot because cobot is something that is still called as a new thing in robotics. And it is very much oriented towards the objective of this workshop also. It says robotics, IoT, and something, one more term was there now. Autonomous, yes. So it is very much into that purview. So that is the reason I am covering this. And definitely it is a subset of use robots. So it will cover in broadly it is robot. Okay, so let us begin. So yes, these are few things that I intend to continue. Depending on your interest, I may divert a bit. Okay, I may divert a bit. Okay, and maybe few more examples. More than this, I may cover if at all you allow me to do so. Okay, so collaborative robot as such, it is intended to work direct interaction with human. Direct interaction. Whatever robots you see so far, they are caged robots. No? They are caged. If you at all have been to any industry and seen a robot working there, they are mostly caged. Okay, so what you will find that robot is isolated in a cage. There is a gate with a interlock switch. As soon as you open that gate, a robot stops or slows down. Why that is required? Because robots are weak. Okay, they are weak. They are just like our arms, no? They are no more like a star moving thing. ना robot humanoid के जैसा नहीं दिखता. You must be knowing so far, no? इतना तो भेद खुल गया है ना? वो सपना तो टूट गया, है ना? So robots are no more like human. They exist only in movies and in industry. It is just like a arm. एक हाथ है, उसी में आँख भी लगा दी. We call it hand-on eye or maybe eye somewhere in a fixed point. Okay, so that is how robots are in the industry, and that is the most common way of using industry, right? So that is the reason this cobot came in. Because of that kind of thing, we want to do our job, day-to-day job. Pick and place is not much of a difficult task. It is a day-to-day job. Okay, इधर से उठाना इधर रखना है. Whole of the day, it keeps on doing that. You call it dull, dirty, dangerous, and difficult, ना? सुना है कि नहीं? ऐसा कुछ होता है डल टास्क यू इंटेंड टू यूज रोबोट डर्टी टास्क रोबोट डेंजरस hazardous area robot dull dirty dangerous and difficult task very heavy payload you want to use robot तो dull dirty एक और डी भी है तो ये सब के लिए रोबोट यूज करते हैं so that's quite lot of monotonous task you want to put it to robot and normally standard robot were working in a cage. Scenery was very different. If you get in, robot used to stop. If you have to maintain it, it is very difficult to get into that area. Whole of the assembly line needs to be stopped at times. Even in a simple small breakdown. No? So that was the problem. So now with cobots, no? So quite number of times you don't need huge robots to do that job. At least for at least 5 to 10 kg, 20 kg payloads can be easily handled with a smaller robot. Rather cobots nowadays. So what exactly it is meant to do is to work along with the human without having any potential safety systems all around, right? And you have to be with it. So humans do exist with robots. They work along with the robot. So there are different level of collaboration that each type of robot allow. Okay, so that is what we are going to cover in cobot. Okay, this is me handling one such robot. Okay, so these are few terms which are defined by IFR. IFR is here, International Federation of Robotics. Four level of collaboration is defined. It is coexistence is there. coexistence. Robots, they exist with humans, right? They alongside remain with humans. They keep working, I keep working along, just like two humans are working together, right? There is no fences, there are no shared workspace also. As long as shared workspace is not there, you work in a region which is, let's say, 1 meter radius, you are working like this. What is there in another 1.5 meter radius, it is working. Both are not overlapping, it is perfectly fine. Nothing wrong is going to happen. Okay? But yes, accidentally you may enter into that workspace and accidents do happen. Okay? So maybe I can give you one few example. uh, Incident newses are there. There are many robot news which are published. I don't know why it is opening here. Okay, इस तरह के बहुत न्यूज आते हैं. Just see, fatal accident summary, die casting operator pinned by a robot. Right, तो ऐसे कई accident reports हैं. So that I may share with you all. That is published time to time at various journals also. So that type of news do come quite often. It is circulated to industrial soft flow. एक एक्सीडेंट होता है, उस सारे इंसिडेंट रिपोर्टिंग में सारे जगह सारे इंडस्ट्री में न्यूज की तरह फैलता है ना? जैसे पॉलिटिकल न्यूज, धर्म का न्यूज हमारे पास पहुंचता है, उनके पास वो पहुंचता है. ठीक है, तो that is very important news. You should learn from that. That is the reason. So this should not happen. You should coexist with human. Sequential collaboration, sequential. How these things were handled earlier, it was sequential. You do a part of a job, robot does the remaining job, another robot may be there, again a human is there. It's a sequential job. Most of the time in agro food packaging industry, this type of applications are there, जिसमें sequential से काम चल जाता है. I hope I am mixing Hindi in between. You are okay with that? Anyone from South? यहाँ सीख गया, एनआईटी में आके ट्रेन हो गया. वेरी गुड. अदरवाइज सोनिया गांधी विल विन. हाँ, सी लर्न बेटर. हाँ, okay. So agro food packaging industry, this kind of job is quite common when 100% of the job cannot be handled by the robot. That is the place you require this type of mixing environment where sequential collaboration is quite okay and people go for it. Then comes collaboration when both of them are in motion, like transportation. Right. The way the picture is showing, a robot is handling a part of a cot. Sometimes even in hostel, what you do, you shift a cot from one room to another. How do you do that? Just recall that event, no? What you did, no? One of you just lifted it up, another one lifted from the other side of it, and then what happened? He became a master. One of you become a master. He drags you. You just follow based on the forces that you feel in your hand. Am I right? You don't know where to go. You can see the actual path. He went out first. I am just following you. So what you do? You just follow based on the force input that you get in your hands. Or sometimes through visual servoing. You just servo him. He goes somewhere, you go there. Right? Providing some collision with obstacles. Right? So that is how it is operated. So that kind of job is normally not possible with standard robots. Why? I'll tell you very much in detail in today's talk. Okay, and then we'll talk about cobot also. So cooperation is very much required in the industry. Sorry. And then you have responsive collaboration. What is responsive collaboration? A robot is very much active. Like you want to insert a key in a keyhole, right? So how do you do that? You actively feel the forces, adjust your positions based on the forces that you see, and even in the dark you can do that. गाड़ी चलाते हो, अंधेरा में पार्किंग में गए हो, you can insert the key even without any vision guidance. It is purely force guided way you can do it. You can see through your fingers, right? You feel the forces, you do it. So that kind of potential is there in cobots, and that is what makes it very much applicable to industry nowadays, modern industry, right? So that is the reason. So that kind of active collaboration is possible with cobot. So these are the four things that you should know why cobot do exist in the industry. Okay, and there are various levels of collaboration. IFR has defined this also. Okay, in 2016. So most of the cobots that we see fall under this. This was your earlier robot when you have a friend, human is outside, robot is inside, it does its job. This is what there is no fence, but yes, there is no overlapping workspace also. Okay, both of them can work simultaneously. Over here, you have sequential collaboration, but there are some overlapping workspace. You can give a part to robot can take it first. This is where most of the collaborative robot exists, and this is what we intend. These two higher up. Okay, robot and worker on the same part. Both of them are working on the same part. Both of them are active together. That is where highly probable that accident do happen. Right. So that is what we want to avoid. Even if it happens, it should not offer too much of damage to the environment. Right. So that damage should not be there. So that is how robots are designed so as to do these kind of tasks without doing any damage to the environment. Environment here is not environment outside, it is industrial environment where you have quite precious things lying all around, right? And then you have robot response in real time. You can drag a robot, make it do something, just the way you drag when you shake hand with someone else, right? Handshake याद है? Handshaking कैसे करते हो? फिर recall करो इस event को. One of you become a master most of it. Other one just shakes it along with you. If both becomes master, you won't be able to shake hand, right? हाथ मिलाना भी इतना सेंसिटिव चीज था, कभी सोचा था? हाँ? होता है. रोबोट से करवाओगे, you will feel that it is really a difficult task, right? It is a difficult task, even shaking a hand, right? So that is what this kind of collaboration is required, and that is where cobot again gets in. So we want to reach here. We are here. This was the earlier situation. These are the levels of collaboration. Okay, why do we need this? Yes, accidents do happen. What kind of accidents which predominantly happen in the soft floor is impact, direct impact. बहुत dangerous है. They will simply kill you. No way out. You can be saved. Okay, and pinching. Sometimes pinching means your finger may get trapped in between object and the robot itself. Pinching can happen. Pinching, just like pinching. Okay, trapping accidents. Sometimes you get engulfed within the robot arm and you are trapped. You cannot come out. It can squeeze you. Toothpaste के जैसा सब बाहर आ जाए. ठीक है? कार्टून थोड़ा इमेजिन करो, मिक्की माउस में होता था. ठीक है? वैसे ही रोबोट तुम्हारे साथ कर दे. ठीक है? So that is trapping accidents. And then you have compliant task. Compliance is nothing but ability to conform to the will of others. That is what the dictionary defines it. Ability to conform to the will of others. How others want you to do. Have you ever been to a Durga Puja pandal or somewhere? क्या होता है? You have an objective. मुझे दुर्गा जी देखना है. ठीक है? भीड़ है पूरा चारों तरफ. There is no way out. You can go there. But you keep driving yourself somewhere. भीड़ थोड़ा इधर धकेलेगा, थोड़ा उधर धकेलेगा. Finally you reach there, right? So you are conforming to the will of others, but you have a definite objective when you reach there. The same way these robots are operating. Okay, they have an objective. It will do that, but it is conforming to the will of everything else which are around, right? Okay, so that kind of task, one of such task is an assembly. Any problem? Okay, assembly task. Assembly task is similar thing when you are constrained by something. Like I want to open a door. Right, I want to open a door. I don't know the exact trajectory. If I am holding the handle of that door, it is bound to go in a circular arc. Am I right? In circular arc में जाएगा. But the coordinates of that, I don't know my own brain. I don't know where that coordinate will lie. No, it is bound to go in a circle, right? So what I do, I simply pull it. I simply pull it. So what does happen? What happens? you are compliant enough to take any inaccuracy in that circle, right? Any inaccuracy is taken up by your compliance, and you just allow yourself to go in a particular direction, not necessarily in a circle. Ultimately, you achieve what you want. Opening a drawer is similar. You don't know the straight line equation in your own coordinate frame, but you are able to open the door. So those are some of the applications when such robots are quite helpful. Similar is any assembly task. You are inserting a pen in your pen ka cap, right? Or cap in your pen. Both are similar. Well, that is known as a peg in a hole task, where your hole is not known and still you want to insert it, right? And you are running in a guided manner governed by some constrained forces, right? First year engineering mechanics, सभी ने किया है ना? All of us are engineer here. At least physics you know. Na? You don't need to be engineer also. Robotics is such a beautiful subject. You need not to be an engineer also, right? It runs only with vectors, matrices. That's all. Engineering mechanics, physics is quite good enough. If you know that, you are done with your prerequisites. And you can start doing robotics to this level. I'll tell you each and everything you will grasp. सब कुछ समझ में आएगा. And mind it, this is cobot, this is not even robot. And you will understand most of it. So that is what is robotics. Okay, so assembly task, surface finishing task. Again, surface finishing task like grinding, polishing, buffing, deburring, whatever this kind of task. What does it do? Basically, you have to maintain a constant force against your surface. जिस surface को grind करना है, polish करना है ना? उसके against एक constant force maintain करना है. Why? You want to grind it uniformly all over. Is it not? If at all your forces are varying, you will make a pocket somewhere, maybe, right? Or it will be grinded uniformly, right? So that force is to be uniform all over. Without knowing the equation of that surface, you have to polish that surface. How that is possible, right? So that is what we are going to learn today also. इतना कुछ पड़ जाएगा आज निकलने के बाद इतना कुछ जान रहे होंगे देखते हैं okay cooperative manipulation again similar to the task that I have shown you have to cooperate with environmental objects or two robots can cooperate right so those kind of tasks human robot collaboration it is not always robot that collaborate with another robot sometimes human and robot do also collaborate together do some certain kinds of tasks okay yes safety of the robot and its surrounding these are some of the reasons why cobots do exist safety obviously that is first this kind of accidents which are mentioned here should not happen right so for that reason cobots are there now let us quickly see what was a theoretical difference between normal industrial robot and this robot right so these are some additional requirements apart from standard requirements which was there in industry apart from IP class ingress proof and those such things standard industrial machines do also have some standards they follow apart from these two these are specifically for performance criteria for robots this is for safety of machinery it is in general any robot follows these two ISO standards apart from this cobots do follow all these जो टेबल में है right so it has so much of additional standards to follow. Two of them are machine directive, safety of machinery, robotic devices का special safety requirement है. Part 1 and this part 1 का एक और type है. Robot devices, collaborative robots have got special ISO directives which is there. Okay, so these are some special things which are there. Actually nowadays what happens now because cobot is evolving we are being fooled by manufacturers like anything. They sell anything in the name of compliance to you. They'll say any robot, they will call it as a cobot and they can sell it to you. If it is compliance, that doesn't mean it is a cobot. If it can follow you, it again doesn't mean that it is a cobot. So they will demonstrate two things to you which appears like a cobot, but they are not tested like cobot. So cobot should not damage your fingers if it collides with you. Sometimes it should be sensitive enough to detect your touch even, right? So they are so much so safe, okay? But these cobots, what we are being sold, uh, it is not in that category. So they are not certified with all these. They are mostly certified with this one only. That is repeatability test, which is there with most of the industrial robots. So they are just another industrial robot without qualifying all these. Okay? So beware, if at all a cobot reseller comes to you, reseller, it is not a seller, even, not even a manufacturer. They are just marketing guys who can market anything to you. Be careful, if at all you are into industry or doing robotics, everything is not a cobot. Beware, these guidelines should be taken care of by any cobot manufacturer. Okay, I hope I am not too much monotonous. If at all there is a monotone, break me here, tell anything.
No, so people are enjoying.
Really?
Yes, sir. Few of them said me, that's why.
Really?
Yes, sir.
वो तो कंप्यूटर कर रही है.
हाँ सर, एक्चुअली दे आर वॉलंटियर्स, मैंने कुछ कुछ छोटे मोटे वर्क्स दिए इधर.
Volunteers are exempted.
नो सर, इट्स लाइक दे आर आल्सो
You
नीडेड.
also can learn.
प्लीज आप लोग,
We need not to be a participant to learn.
प्लीज आप लोग बाद
And there is no age to learn. Huh?
यस सर.
There is no. You may be first year, they are exploiting you.
यस सर, दे आर ऑल ऑफ फर्स्ट.
Yes, I know that. That happened. Anyway, no problems. अब मुझे पता है. ठीक है, okay, very good. I need time. हाँ. See, yes. I am happy with that. If you give me, I am whole day here. So the way I discuss now, even in class, I feel always short of time. Time कम पड़ जाता है. Robotics इतना interesting है. If you discuss now, if it is 2 way, it is even 1 day is less. So anyway, hope you are truly enjoying. So yes, let us move ahead. So these are some of the criteria that I have told. So stop me whenever you want break. We'll have a break in between where we can have informal talk. This also is informal. I am not teaching anything technical so far. Right. Okay. So now collaborative modes as per ISO and ISO. Two ISOs that I have mentioned here also. There are few collaborative modes. One of them says it is purely manual. When you can drag a robot, you can make it do something. This is manual. Monitored and safe stop. In this case, you have to stop the robot manually from external switch or through automated switch. If you enter into the workspace, you have to stop it. Only manual. Then came this type of robot which is having some safe stop. It is monitored by some kind of sensor when it can stop automatically if you enter that workspace. Maybe through limit switches, sometimes through proximity sensor, right? Or there are some distance and speed monitoring also is there. You can also monitor the speed using. If you are approaching the robot very fast, it will stop even much before it is normally supposed to stop. It also detects your velocity, not just your position where you are. Right? So they are more probable they will hit the robot. So it basically has to deal with probability of hitting the robot. Right? This is one. And finally this one. This is actually a cobot category, which are force and power limiting. If at all you, even if you hit intentionally, they cannot deliver more than some amount of power and they won't do that much of damage. Right? Collision हो भी गया, इतना डैमेज नहीं हो. ठीक है, एक आदमी आदमी से टकराता नहीं है. होता है कई बार एक्सीडेंट स्पोर्ट्स में होता है, सब जगह होता है, फुटबॉल में होता है, कुछ होता नहीं है ना. वी कीप प्लेइंग. So same way with this kind of robots also, they are limited by power which it can deliver when it encounters any sort of collision or accident, right? So yes, there are many other things which I can discuss about. A few of them are risk assessment and avoidance. So if at all it has encountered any accident, what is the extent of damage that this robot can do? You can classify this robot in that category. So these are two tables which are very important. Table 1 and 2. This table I'll share with you This may be of interest for some production guys, right? But not necessarily for this talk, so I am exempting it here. Okay, these are very important tables which can tell you what is the extent to which this robot can damage you, or if any accident has happened, so where did it lie? उसका evaluation कैसे करें? ठीक है, anyway, so we are skipping it. So these are few applications. Now I am getting little bit physics out here. Okay, when can we apply force? If I am moving in space, free to move, can it apply any force? My arm, my hand, does it feel any force if I am moving freely in space? If it is free to move, it is not bounded, right? So it cannot apply any force. Is it not? Until unless it is constrained anywhere, it doesn't generate enough force. The robot generating a force in free space is meaningless. It is only to drive its actuator, take up its own weight, but for an object that it is holding, that object is not getting obstructed anywhere, it is not generating any force. So normally an object, if it is maneuvered in space, it has how many degrees of freedom? 3. कितना दिन हो गया वर्कशॉप? वर्कशॉप पर क्यों? सिंपल फिजिक्स 6 डिग्रीज होता है ना, क्या क्या होता है? 3 ट्रांसलेशन 3 रोटेशन, राइट? So as many number of constraint you put, as many forces you can generate. Forces here I mean forces and torque. So generalized force, right? Generalized force. Okay? So like writing on a board with a robot. Why with a robot? Even if I write it like that, so how many forces I can generate? Just one, because I am constrained to move along vertical direction. I cannot get into the board, right? So that is the only constraint that my hand sees when I write with a chalk on a blackboard, right? So that is the only force that I see. If perpendicular to that surface of the board, there will be a force. Is it not? वही एक force होगी. बाकी it is free to move along XY plane of the robot, है ना? So there won't be any forces along this. There will be some partial constraint is there, that is friction, right? So for a small amount of force will be required. Ideally, there is no force along XY, only along Z. It is free to rotate in any of the directions. So effectively just one force is there. The rest 5 degrees are free to move. So this chalk has now 5 degrees of freedom. One is constrained, one force is there. This is one example of that. We tried doing it with a robot, right? But normally to maintain that force, constant force, otherwise your chalk will break. So you need to have a force sensor at a wrist somewhere over here. So that can feel the forces. You can create a closed loop and you can, using that feedback, you can control that force, right? 2 Newton, 3 Newton, जो भी चाहिए उतना exact उतना amount of force you can maintain, or you can have some additional compliance. You can just, without having a sensor, you write with programming position controlled robot, and you can have a spring which is fitted at the end. Forces will not be uniform in that case, right? But you can manage to write some. This is one example. Next, inserting a peg in a hole. Constraints देखो कितने हैं. एक होल में पेग को इंसर्ट कर, ठीक है, जैसा दिख रहा है. Hope it is clearly visible. This is a block with a hole. You have a pellet which is to be inserted into it. Constraints क्या क्या है? Once you get into that hole, you cannot move along X, you cannot move along Y. That one, right? You cannot rotate along X, you cannot rotate along Y. कितना constraints हो गया? 4 constraints. 2 are free. You can vertically go up and down. You can rotate about the same axis. 2 are free. So इन दोनों में free है. But as long as you are searching that hole on the surface, how many constraints? It is just like a blackboard, right? So as long as you are searching the hole, you are free to move. You have just one force that you will see. But as soon as you get into the hole, 4 constraints, 2 forces remain. Forces here I mean force and the torque, right? So that is one example. Next one is, this is one example, like a visual surveying. No, you need this kind of robot. Why? Vision systems are not very accurate. Even when you have approached a hole of a lock, you want to insert a key. क्या हो रहा था उस समय? You saw very precisely. You thought the hole is there. Every time you reach there, you are bound to hit. You cannot insert the key directly into the hole just by seeing it. Can you? ऐसा कोई दिलदृष्टि तो है नहीं. Right? The nearer you go, yourself, your arm, your fingers will occlude that hole, and you won't be able to see it also. Sometimes, right? Occlusion हो जाएगा, दिखेगा ही नहीं, hole ही नहीं दिखेगा, तेरे ही हाथ से ढक जाएगा. हाँ? So that is the reason. Right? So vision systems are not very accurate. So in that case, you are bound to hit the surface. If you are bound to hit the surface, your robot should be compliant enough to take up those forces. Huh? Normally, industrial robots, which is of 200 kg payload capacity, 500 kg payload capacity, do you think they are compliant? They are not. आधा ग्राम की फोर्स को डिटेक्ट नहीं कर पाते. Forget about this kind of forces. So they are very dangerous. You program your robot to insert a key and it fails badly. It will either break the key or it will break the lock itself. Do something. Except inserting the key into that hole. Right? It can do everything else. Okay? So vision systems, they require this kind of thing. Exoskeleton, you all must be knowing it. Exoskeleton क्या होता है? People don a kind of mechanical thing with some kind of sensors on their body, right? So whatever you do, it records that motion live and directly it transfers that data to the robot and robot does something. Use कहाँ पे होता है? कहाँ पे होता है? One application for which we made this at IIT Delhi is to handle nuclear pellets. Nuclear pellets are radioactive thing. Robots are placed in the hot cell where nuclear pellets are there. Person stays outside the hot cell. They can see through a wall which is very very thick, 1.5 meter thick glass होता है, वहां से दिखता है, and you can wear exoskeleton and it makes the robot move and pick up that pellet, insert in a hole, do whatever, right? So this is one application. Again, there is some coordination difficulty is there, some latency is there, some inaccuracy is there. So that pellet is bound to hit somewhere. And pellets are made up of sintered metal powder, uranium. Powder means if at all it hits, पूरा surface पे powder आ जाएगा uranium. It is very dangerous. You cannot pick it there. So it should not happen. So it is such a difficult thing to do, and we intended to do that. So that is the reason you should have some sort of compliance there. There are forces to detect that. So this is one possible application. Hazardous task, you say. This is one hazardous task which robot is doing here. Okay. I'll tell you, there are many hazardous tasks near to this city. If you are here in Jamshedpur, you are in a heaven, I tell you. गरम लगता है जरूर summers में, but you are in a heaven for engineers. This is heaven. I tell you, every summer you can visit a plant somewhere. You have n number of industries. Summer छोटा पड़ जाए. ठीक है? You have more than 7 to 8 international companies which are existing in this land. Right? So you just go there and see why robots are used. Answers अपने आप मिल. Right? One possible application that I have seen at Bokaro, it was nothing but a centering. It was a plant galvanizing plant, and क्या होता है? Zinc molten bath है, and you have a sheet that gets in. It comes out of that molten bath. So that जो metal sheet है ना, इसके ऊपर एक layer of galvanizing जानते हो, है ना, उस sheet के ऊपर आएगा. But that molten bath gets oxidized due to the air, है ना, उसके ऊपर एक skimming हो जाता है. मलाई जैसे दूध के ऊपर बैठता है ना, उसके ऊपर भी मलाई आने वाला नहीं, बहुत गर्म होता है. ठीक है, तो ऐसे करके डूब के निकलेगा. अब क्या हुआ? That malai used to deposit on the surface. If you don't skim it, मलाई निकालोगे नहीं, तो वो सरफेस पे सटेगा, सरफेस विल बी नॉट यूनिफॉर्म एंड विच इज वेरी बैड सरफेस यू विल कम आउट विद. एंड सो देयर इज अ पर्सन होल डे 4 आवर्स उसका ड्यूटी होता है, फायर सूट पहन के मॉल्टन बाथ के आगे खड़ा रहता है, एक स्टीमर लेके ऐसे ऐसे दिन भर करता है. इतना डेंजरस टास्क है. मॉल्टन बाथ है, गिर गया तो गया. जिंक का वेपर ऐसे भी प्रॉब्लमेटिक है, टेम्परेचर न जाने कितना है और पूरा दिन उसको करना है. And this task is quite easily done abroad. Quite a lot of companies are doing it. With KUKA robots, I have seen one application is there. क्या करते हैं वो लोग, विजन प्रोसेसर ऊपर लगाया है, सेंसर लगाया है, स्किमिंग को डिटेक्ट कर लेते हैं. एक रोबोट ऑटोमेटेड वे में स्किमिंग करके साइड हो जाता है. थोड़ी देर के लिए प्लांट स्टॉप हुआ, स्किमिंग हुआ, फिर प्लांट स्टार्ट. इतना ऑटोमेटेड हो सकता है. यहाँ पे भी है मैनुअल, सभी जगह मैनुअल है. इंडिया में 90% मैनुअल. आई डोंट नो कहाँ पे ऑटोमेटेड है. ठीक है. दिस इज वन एप्लीकेशन. एक और एप्लीकेशन यहाँ ब्लास्ट फर्नेस. You have a robot, a simple human being who is there standing doing sampling, XRD analysis. सुने हो? मेटलर्जी का तो यहाँ भगवान बैठे. मेटी जमशेदपुर है ना, यहाँ तो है बहुत. तो क्या होता है, वो XRD एनालिसिस के लिए सैंपल्स कलेक्ट करते हैं. लैडल में पोर हो रहा है मॉल्टन लोहा, एंड यू टेस्ट सैंपल इट, टेक इट फॉर XRD एनालिसिस. 2 आदमी फायर सूट पहन के वो मॉल्टन बाथ के पास खड़े, लोहा पिघला हुआ लोहा एकदम रेड हॉट, and people are standing just to collect that sample, taking it, doing XRD analysis 4 times a day minimum. Every pore is to be analyzed. ठीक है, वो कंपोजिशन को चेक करते रहते हैं. You see, it is very dangerous, sir. When I went there, I could not stand there. 2 आदमी फायर सूट पहन के वहां खड़ा रहता है.
मैंने एनिमल और इसके कोऑर्डिनेशन, किसको कोऑर्डिनेशन में 96 में ये काम किया हुआ.
कितना डेंजरस होता है देखो.
बहुत dangerous है.
एक बूंद जो उसका काफी है, शरीर से इधर से घुसेगा, इधर से निकल जाए. हाँ, and people are standing there. So you need robots for all those reasons. Anyway, थोड़ा सा divert हो गया. So that not necessarily a cobot which can go there. Ordinary robots are required. So that is where it is required. This is one possible application. When you have a 3D screen in front of you and your robot is handled with a 3D glass, person is wearing a 3D glass. This kind of application is there in a teleoperation surgery also. रोबोट से जो सर्जरी दूर बैठ के करते हैं ना, वहां पे होता है. ठीक है. तो इज होल्डिंग अ हैप्टिक डिवाइस. दिस पर्सन कैन फील द फोर्सेस. दिस इज नॉट लाइक अ माउस और अ जॉयस्टिक. दिस इज अ हैप्टिक डिवाइस which it is this person is using to command the robot to go to a certain place. So it captures the position here. Real robot का view यहाँ पे मिल रहा है. This is a simulated environment you can see, and with wearing a 3D glass. So there is some imperfections which are there that is to be taken care of, because there are latency, there is inaccuracy, vision में problem है, view में problem है. So due to that, robots always hit somewhere, and to take care, you have robots and force-sensing robots. This is one similar application. A pellet is picked up, haptic device, using haptic device, it has to be inserted in a pocket. So there are very similar things. So how it all evolved? Yes. Robots, it is started somewhere over here. That is robot with force controls must be somewhere over here. You can take a click. I'll share you this pic. Need not to note down. But around here, active force sensing came in. Right, cobot started evolving over here. This is the red dot. When first time admittance explicit force control was done in the robot, okay, and direct control of force was obtained using any standard industrial robot with a force sensor which is fitted here. Then we have fuzzy thing, and then different types of controller. This hybrid. Craig ka book mein this is there. Hybrid controller is there. Standard robotics ka book. And then now it is a textbook matter. Now you have Khatib's model, and multi-contact model is nowadays there, not just one contact, multiple contacts. And then you have AI ML based approaches that should go. Okay. So this is where almost like physical thing ended, and then AI ML took over. Okay. Then there are many new reportings on impedance control and others. So this is a brief timeline I'll share with you. So yes, it was invented by Edward Colgate Peshkin of Northwestern University, that is the cobot, first cobot. Then US patented this named as cobot was filed. Company called Robotics, founded by Colgate. Cobot, that term, maybe due to that, I don't know. Yeah, but it is collaborative robotics, basically, robotics. Okay, Colgate and Pishkin, these two fellow, right? And then 2003, Stanley Assembly Technology, they acquired the company Cobotics. Follow-ups, then multiple companies, they started making it. Okay? So now almost all big companies, they make such robots. And Severs, we think there are many other research robots and other robotic companies making it. They claim they are make robots, not necessarily they are robots. They may not be certified 100%. Except okay, certification बताया था. I haven't seen certificates for quite a lot of this. We think may have some. That is the MIT development. Others I don't know 100%. And this should be noted here. In 1990, Prasad Akela, he is an engineer at General Motors that time, 1990s around. Okay, he was the first person to take up this patent. He was a IIT Madras graduate. So see, we are not quite far off. We should not be quite far off from this. It was started by an Indian, and then we are lagging behind, right? So anyway, so this is a good thing to note down. And then you have transition in technology. It was passive without a sensor. You had a spring mounted at the end effector. Robot does something and it is cushioned and it takes up any sort of inoculation. That is okay. Then came active sensor, feedback loop. Then came different algorithms to use that feedback in a different way. Then intelligent AI, ML, and those techniques came in. Adaptive techniques came in, and now it is advanced machines which are being used. Right, which is even higher. They are learning things also. Right. So yes, what is the fundamental difference? How they have made cobot possible? What is the fundamental difference? From here, little bit of technical is there, but it's still a very good physics only. सब ठंडा है ठीक है एंजॉइंग स्टिल बहुत तो भाग गया मैदान छोड़ के वॉलंटियर्स भूख लगा वॉलंटियर्स हाँ वॉलंटियर्स निकल गए तुम्हें छोड़ दिया अकेला ओके ना रियली हाँ continue okay so there is one fundamental difference if you have seen a simple link hanging from the a point तो याद होगा ये फॉर्मूला बहुत दिनों से देखा है this is a link this is the mg4 which is going to come two components mg sin theta and mg cos theta what is the tension in this rod it will depend mg cos theta mg cos theta that causes the tension is it all there is centrifugal force also if it is moving centrifugal force is also causing tension is it not there are two okay anyway so this is the one which is responsible to create torque at that joint so robot is nothing but a series of links one after the other एक है link joint and finally it terminates am I right terminate होता है क्या सब robot a robot is a serial chain which finally terminates manipulator now it is not always true you have seen playing lawn tennis देखा कैसे चलती है she stretches her hand if she has to reach more she plays it like this if she has to apply more power what does she do she holds her racket like this दोनों हैंड से पकड़ is it terminating it becomes a closed serial chain दो serial chain ऐसे पकड़ लिए it is not terminating this becomes the end effector in that it is a parallel manipulator normally it is a serial manipulator so serial manipulator terminates each link is like this and then there is a torque. So there are two approaches to drive a link. Two approaches. I don't know what I have written in this slide. Let me just check. Okay, इसको बाद में लिखा है. ठीक है. There are two approaches to run this link. First one is you just have a sensor there. I want to take it to 30 degree to so. Okay. I'll keep on moving this. If somebody from electrical, they know it, it is screw controller, you can do it. You take feedback. As soon as it reaches there, you stop. Sometimes it will overshoot. You have to bring it back. May overshoot this way while bringing back. You have to come back. Finally, it can maintain a position, right? So that is a strictly a position controlled robot. Is it not? Position controlled robot में यही picture. It will try to reach to its position. It will apply 100% of torque to reach to that position. If that torque generating actuator is very, very powerful, like a 250 kg payload robot, so you can imagine how much torque it can apply. So if at all it needs any kind of obstacle in between, it will break that because it runs purely on the feedback of the joint angle. So it tries to servo it to the commanded joint angles. Any obstruction in between will break it. It will break the robot itself or it will break the obstacle. Is it not? कुछ तो होगा. ठीक है? That is one way of driving it. So most of the industrial robots are driven this way. It is very dangerous. So what is the second way of doing it? अभी ये फिजिक्स बताने का रीजन था. How much the torque should come at 30 degree? mg sin theta into L by 2. Provide exactly that amount of torque. What will be? Will it reach there? Of course, it will reach there. It will exactly go to 30 degree. Because I haven't provided torque more than that, it won't go higher. It will exactly stop there. And how much is the torque? Exactly mg sin theta into L by 2. So any obstacle will create more torque. So how much buffer does it have? Let us say it has reached here and obstacle came in. So this is the only error that it has. So that is the only additional torque that it will apply to go to its place. Damage will be minimum. Is it not? So that kind of any link which is driven by torque, not by position feedback, is very, very safe. So all the cobots, there is a fundamental difference. It runs not by the joint angle, it runs by the joint torque. Torque से चलाएंगे, will be safe. Is it true all the time? Any query here? सवाल उठनी चाहिए, physics है. सही है ये? सब बोला सब हजम हो गया. हजम नहीं होना चाहिए, दिक्कत है. लंच का टाइम है, भूख लगा, कुछ भी खिलाओ खा लो. हाँ? नहीं, यहाँ थोड़ा सा मुश्किल है. See, if this is the torque that comes at this angle, this also comes when it is like this. It is pivoted here and it is 30 degree like this. So it has two different positions for the same torque. Is it not? It can be balanced here, it can be balanced on the top also. So that is also to be taken care. So it should have a complete model of the system, including the moment of inertia, so it not just includes the static torque in its model, it also includes the dynamic torque, it also includes the state of the robot, many other things. Finally, it freezes its torque. When it is driving the robot with that particular torque, it has complete information about the robot. Robot moment of inertia, robot statics, right? Complete detail. Okay? So you need a complete knowledge when you make a cobot. Cobot runs on this. Now you know what is fundamental difference, right? It torque sensor at the joint is a prerequisite to make any cobot. Okay? So forget about the days when you used to have joint sensor only, angle sensor. Now you also have a torque sensor. Even cobots, they do have torque sensor as well as position sensor to confirm whether it has reached there or not. Okay? Okay. Now you can see the equations. Equations are not mandatory to understand the physics of it, but still, this is the torque, this is the joint angle errors, proportional gain, velocity error, velocity gain, and integration of sum of error over a period of time, that is integration gain, and that is the driving torque. PID controller based on the joint angle, okay, joint angle feedback. Desired commanded and the actual. Desired, this is actual. ठीक है, ये स्टैंडर्ड तरीका है ड्राइव करने का पीआईडी कंट्रोलर से ज्वाइंट एंगल से दोनों. So this creates a huge torque, as I have said. Full effort to reach to the commanded position. Cobots, they run on position control as well as torque control or purely torque controlled servo actuators. Equation here is something like this. Your torque is not governed by this, your torque is governed by this. इतना fundamental difference है. And this is simple physics. कोई बड़ी बात नहीं, ये इक्वेशन सब लोग जानते हैं. ठीक है, जानते हैं कि नहीं पता नहीं, सुनना इंजीनियरिंग मैकेनिक्स में पढ़ाया था. It has, this is inertia component. I theta double dot is torque. High school physics. थोड़ा तो ऊपर आया इंजीनियरिंग मैकेनिक्स फर्स्ट ईयर. Coriolis and centripetal component. This is gravity torque, static torque. Even without moving, this is the torque that is going to come here. Right? So this is total torque equation. And find it, this is the matrix. This is gain matrices. You have set of torque for all the joints. It looks simple, but it is actually a dynamic equation of motion of a robot. Written in a very compact, easy way. Right? Okay, so this is how cobot works. So torque in excess due to any obstruction is limited, and beyond that it will simply be stopped. So this is a fundamental difference between a cobot and a robot. काफी क्लियर हुआ? मजा आया? मजा आते रहना चाहिए, नहीं चलेगा नहीं. हाँ हाँ, ब्रेक दे देते हैं. दे दीजिए ऐसे ही. चलो लंच के बाद भाग जाएगा, लंच मत दीजिएगा. पढ़ाई में भी कोसाइन सेम है. fully recorded up, what? You are
Yes, live stream.
live stream कर रहे हो?
It's been recorded also and live stream also.
Oh, it will remain in the YouTube.
Yeah.
Yes. Oh.
सुनो ना, टी ब्रेक लिख दो जल्दी से. स्ट्रीम में टी ब्रेक लिख दो और कोई टी
तो बोलना चाहिए था ना, मंदिर मस्जिद वाला बात नहीं बोलना.
नहीं सर, कोई दिक्कत नहीं सर.
म्यूट कर देंगे सर अपना पार्टी.
हाँ
क्या पे सामने
नहीं, हम लोग को ना टीचर को आदत होता है कैमरा के आगे नहीं पढ़ाते हम.
हाँ सर,
मेरे स्टूडेंट को मारेंगे.
सबमिट करना रहेगा तो
ऐसे ही है.
तो हम लोग सोचे वही बेस्ट ऑप्शन है.
नहीं सही है, ठीक है चलेगा. अभी कुछ बोला नहीं ना ऐसा वैसा.
नहीं सर, सर बहुत अच्छा लगा सर. मेरा तो यही कोलैबोरेटिव तो बाकी लिखूंगा.
अच्छा कोलैबोरेटिव देखना, अभी आगे बहुत ठीक है.
अच्छे से
कॉपी पे ठीक है बोल. अरे चलता है चलो. IoT तो बाद में, पहले चलाओगे तो ना IoT में इंफॉर्मेशन लोगे. इंफॉर्मेशन लोगे बाद में, पहले चलाओगे तो ज्वाइंट मूवमेंट का वीडियो 66 पे एक्सपेरिमेंट ज्वाइंट एंगल तो
कोई बॉडी को कंट्रोल करना है.
पूरा IMU यूज कर ज्वाइंट एंगल देखने. इतना सारा चीज
Because left hand is working
देखो एक खिलौने उन्होंने बहुत बनाया. तो सब कुछ रोबोट बनाओ मिल जाएगा। इस तरह का चीजें जो है ना अभी स्कूल डेज में बनाते हैं। मैं क्या हुआ अभी हाल में बुखारा स्टील प्लांट का ना स्कूल है, वहाँ पे गया था ज्यूरी बन के, वहाँ पे इवेल्यूट कर रहा था। लेकिन तुम लेवल उसका इमेजिन नहीं कर सकते थे। बच्चे बना रहे हैं ऐसी चीजें, पता नहीं कहीं से बनवा रहे हैं। लेकिन आर्डुनो उर्डुनो प्रोग्रामिंग वगैरह करके डेटा लेके और मार्केट में रोबोट बन
डीप रेट है इसमें माइक नहीं डाले उसको खोल देना
जिला लेवल पे सेलेक्ट हुआ फिर नेशनल लेवल पे जितना पेपर में आया तो काफी दूर तक डिफेंड कर लिया। यहाँ तो गाइड को बीच में बोलना एप्लीकेशन ना वहाँ का टेम्परेचर देखोगे 80 डिग्री तब तक 55 डिग्री में सिस्टम कर जाता था। सारा चीज इंडस्ट्री सेंसर इंडस्ट्री ग्रेड का और उस तरह का कम्युनिकेशन डिवाइस उसका लिमिटेशन के साथ तुम कर पाओगे तब वो काम। ये तुमको बहुत आराम से आएगी। मजा आया खिलौने तो वो भी उतना फ्लेक्सिबिलिटी इंडस्ट्रियल सेंसर में है ही। उसके बाद वो टेम्परेचर पे वो तो यही सब है। फाइनली जब इंडस्ट्री डिजाइन कर एप्लीकेशन ज्यादा सुना ठीक है इसके लिए तो चलेगा ही हमारा तो सब चीजें सब्जेक्ट होता है। हाई टेम्परेचर की बात करें तो हाई टेम्परेचर कंपोनेंट ही अलग हो जाता है। हाई टेम्परेचर रगेडनेस और रिलायबिलिटी इंग्रेस प्रूफ वहाँ का डस्ट कितना है सांस लेने के लिए भी मास्क वहाँ ऑक्सीजन मास्क तुम कर रहे हो ना इसे पहले तुम कर रहे हो तुम सपना है ना तो ठीक है फिल्मों में होता है रियल में कभी पब्लिश भी होगा और एक्सेप्टेंस भी और कभी कभी पब्लिश भी हो जाता है किसी वगैरह भी लोगों ने पब्लिश किया है पब्लिश हो जाएगा लेकिन फिर अल्टीमेटली प्रोग्रेस नहीं करना ठीक है किसी करना है पब्लिश करना यही तो मार खा गए हैं ऐसा नहीं प्रोडक्ट में ही मेरा प्रोडक्ट होता है ये कॉन्सेप्ट चीज करूँगा इससे बेसिक से पूरा बुझना मन जंपर वायर तो दिखना नहीं चाहिए इतना अनरिलायबल चीज है 90% चीजें लगाया वो जंपर वायर जो तुम लोग यूज करते हैं निकालोगे तो अंदर में एक कॉपर का स्ट्रैंड सर जंपर वायर से गायब ही है ना खाली कंडक्टर है बाकी में है ही तोड़ रहे अंदर को खाली सिंगल स्टैंड कुछ नहीं है घर में केबल होता है ना इन्वर्स आता है प्रिंटिंग टूल लोग बनाओ अच्छे अच्छे टर्मिनल बॉक्सेस आते हैं सस्ता महंगा भी नहीं जंपर से बनाओ टर्मिनल से बनाओ ये छोटी छोटी चीजें हैं जहाँ पे क्वालिटी जो कर रहा है ना वो प्रोजेक्ट वाला दिन कम करता है बोले सर अभी कर रहे मिल जाएगा हम लोग खुद ही बनाने से जंपर वायर तो खुला वायर खरीदते हैं फिर हम लोग काम करते हैं
और वहाँ अगर मार्केट बेच रहा है तो जरूरी नहीं है को बढ़ने वाला है होता तो उसी चीज को जो है ना एक 10 का वही दे रहा 50 में यही चीज रहेगा इसको गारंटी नहीं है कि 50 में ले रहे हैं तो मांगा
वॉलंटियर सब वापस आ गया
आप लोग इधर आगे बैठिएगा एक एक करके, ठीक है?
वॉलंटियर सब वापस मैं भाग गया था लास्ट था
काफी पैसे
कमर है तो पैसे भी काफी
कौन
इतना बड़ा
अभी तुझे पहले
बिना महंगे महंगे कई चीजें आ गई एक आध तो इस प्रकार की को थोड़ी हर लैब में 90% खराब नहीं ज्यादा काम पैसा है पूरा पैसा तो धीरे धीरे शुरू करते हैं यस लाओ सभी तो
प्लीज सुनो ना, श्रेष्ठ बाहर जाओ, सबको जल्दी से बोलो कि क्लास स्टार्ट हो जाए। फोटोग्राफर चेंज कर दिए बैटरी, इस टाइप के टाइम में चेंज कर दिया करो बैटरी,
ठीक है
चल जाएगा पक्का, ठीक है।
हाँ एकदम फुटा फुटा बोलेंगे सेंसर कर देंगे
हाँ सर वो हो जाएगा सर।
सर रात को चेक करेंगे सर एक बार यूट्यूब फाइनल के लिए, फिर देखेंगे।
टीचर ने तो आना है उनकी बोल एटलीस्ट मुझे तो है
ठीक है
सर वो कुछ कुछ से ही लाइव एग्जांपल से लिंक होता है, तब ज्यादा इंटरेस्टिंग होता है चीज।
एग्जांपल है तो ठीक है
पॉइंट इधर थोड़ा आगे बढ़ो।
अटेंड करो ना. तो डिफरेंस क्लियर है? क्या डिफरेंस है, कोई बता सकते हो? एनीवन?
What? Can you repeat the question, please?
That the standard robot drives its thing using position control mode.
Yes.
Cobot drives it using torque control. Difference क्या है? What do I mean by running a robot in torque control? Got it? तो छोटी सी बात है. Normally I was taking feedback from the joint, that is joint angle. I commanded my robot to go to a place based on the joint angle. I commanded for the angle, took the feedback of an angle, and then compared them. If at all it reaches there, you have to stop it. In order to do so, you have a type of controller. Can be a PID controller. Normally, industrial robot they have that, so it is stopped there. Again, another way to drive it is you have a link which is fully defined. I know its center of mass location. I know its masses, right? Moment of inertia, tensor, not just inertia, scalar inertia, right? So you know the inertia, right? And now you are doing what? You are just commanding to go to a place using a torque command. And I am giving just enough amount of torque so as to reach to a particular angle. In case of simple slender bar, it is mgl by 2 sin theta. You saw that should be the torque which is provided in order to go to any angle. If you provide exactly that amount of torque, it will exactly go there and it will stop. Right? Beauty of this type of driving system is, if at all you encounter any collision from outside, any obstacle in between, robot will stop there because it is not provided with too much of torque to go to a place. It has exact amount of torque to go to that place. Right? Whereas in case of position control, if at all you see any obstacle, it will apply its full potential to go to that particular commanded position. In that, it will break that obstacle or itself it can do some kind of damage or motor will get. Okay? Okay. So this is a fundamental difference. Okay. How is that achieved in a standard motor? This is your standard DC servo motor. Servo motor, it is physically a system which can create a servo motor. As such, it is not a servo motor. People loosely they call it a servo motor. If at all you have a DC motor with commutator, gearbox, and a shaft with bearing. You know this type of structure? खिलौनों में भी होता है आपके लिए, ठीक है? फिजिक्स पढ़ने की भी जरूरत नहीं थी, बचपन में ही देखा, ठीक है? इंजीनियरिंग तो बहुत बड़ी बात है. So you have a DC motor, you have a commutator, and at the back end of it you have a encoder, optical encoder, or maybe a potentiometer, which can give you a position feedback. Wherever it is currently situated, it will exactly give you that angle in relative way or absolute way. But it will give you some sense of angle so that you can take feedback of an angle. So outside of this, you need to have a circuit which can power this device to run at a particular direction, to accept the command and then compare the angular values and stop whenever it is required based on your PID controller or whatever. Right? So that is the hardware. It needs to be controlled with a small amount, with a small software which can compare the data and it can stop. That's it. So it is purely an electromechanical stuff, but yes, this allows driving only in position control mode. So what's a normal robot like KUKA IVA? This is a section view of KUKA robot. Earlier it was a different robot. DLR was known as DLR robot. Now it is IVA robot. So you see the driving system is very, very complex. So now what additional parameter it has, additional parameters that it can sense is, you see you have power supply, power controller board, right? And then you have power converting unit that basically takes input of the power command and then converts it to proportional direction bit. Let us say it is a AC servo motor unit 3 phases, and that can run in clockwise or it can run in counterclockwise direction. So 3 phases are there, and that whole sort of driving circuit is there. Then you have motor, then you have bearings, and you have link position sensor as well as a torque sensor. You don't just have a position sensor, you also have a joint torque sensor. Two parameters are now sensed. And driving wise, it is not just a standard gearbox like this. It has a good amount of backlash. Backlash जानते हो? Gearbox में backlash क्या होता है? There is gap between two gear tooths. If it is meshed like this, while turning, this should be the direction. While reversing, there is a gap. It will stop in between. Now it will start moving. So driving and driven shaft, there is some gap in between. So there is a small amount of time in which there is no movement of the driven shaft, even when input shaft is rotated. Right. So that is a small amount of backlash. Backlash is normally there quite high in this kind of gearbox. This is having a different kind of gearbox known as harmonic drives. Right. So that kind of drives are there which has very, very negligible amount of backlash. Why is it that important? Even a half a degree of error in this, if link is almost of let's say 1 meter, so you see a huge amount of deviation on the top. Is it not? So half a degree is not half a degree. Displacement wise, it can be very high. And in case of serial robot, you have half a degree error here, 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 here. They all will be accumulated together. At the end, you will see this much of deviation. Right. So that is not the case you want your cobot to behave. In that case, you have structure which is very much complex. It is like this. And also you see this robot, all the things that is there from this end to that end, driving to the driven, it is center hole which runs. No? You can pass through all the cables from center hole. Right. So this kind of robot, there is no cables which are visible from outside. It looks very much sleek, beautiful, right? So it passes all from the inside. And you see the controller card, it looks like this. It has a cooling fan also. All the cables you see it is given like this. Right? So this is very, very complex, and that is the reason why it is very, very expensive. A normal robot 5 kg payload, when I bought it for the first time at IIT Delhi, it was something around 25 lakhs for a 5 kg payload robot. At KUKA KR5 Arc robot. And the similar robot of 5 kg payload capacity cobot was something around 85 lakhs. And we were the first one to buy that time in India. 2010-11. Okay, at IIT Delhi, it is still there. So you see, that is the huge cost that we are paying for this technology. Right? Now India is also making it. Few companies are there. So that is the good news. We'll be having probably at IIT ISM Dharwad also very soon. So this is how it is constructed. See? Okay, so this is the associated difference which is there for this kind of robot, and then the cost also. And similar, you see this is one of the links, and another link which is everything is assembled this way. This is the cross section. It's very, very complex, right? It has an end cover also. And here this thing comes out and you can inspect the circuits. So they are very, very complex. Okay. Okay. So there are many other features. Now I'll talk about features. So what does we gain out of it? So if at all robot is compliance, what is the first thing that you get? Forget about the application. What do you want out of your joint? What should be programmable? Okay, I can program for position. What else I can do with that joint? If it is this complex, it gives me flexibility to do many things, right? So why is it able to do that kind of thing? We'll discuss that now. So one of them is very common. That is even any demonstrator who comes and sells a cobot to you, they will be demonstrating this. This is the first thing that is the claim from any cobot manufacturer. By default, they'll show this one. But this doesn't make it complete cobot. Okay, I'll show you what the joint and forces due to all the links and actuators are compensated. Compensated means your robot will behave as if it is in a space. There is no gravitational force acting on it. Right? That means if it is here also now, even when it is not moving, there are torques which are applied at each point. Do you agree? Yes or no?
Yes.
Due to gravitational pull, now that torque will come. So your actuators by default keeps on providing that joint torque at each joint so as to make it float in the air. Right? So any external torque will now make it move, make it very, very flex. Because it is compensated against gravity by exact amount of torque at each joint, it floats in the air. It floats in the air. So it behaves as if it is in a space without any gravitational force. Now all the directions are similar. Earlier, what was there? That what was the problem? It was gravity directed. Like in one direction, it will behave differently, whereas in horizontal direction, it will behave differently. Now, when you have compensated your robot with gravity torques, so your robot will behave equally in all the directions. Is it not? There is no G as it is, right? So it behaves in a similar way in all the directions, right? This allows one very good thing. I'll show you one video here. I hope this runs. Okay.
ऐसा लग रहा है फेस से बहुत ज्यादा ताकत लगा रहे हो सर
Got
थोड़ा
it.
स्माइल
So there was a KUKA person who was giving me this training to make this robot go wherever it wants. So I'm just dragging it to different points, right? In order to teach this. So normally industrial robots are not taught this way. You have to drag it using jogging key. Go left, 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 right, 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 like that. But this one can be dragged. What happened? Okay. So it can be dragged just like this. Just हाथ से ऐसे कहीं पे भी ले गया because it is floating in the air with gravity compensation. So I can precisely take it to any point on the trajectory. Okay. And then I'll just leave it, say go there, it will just track all those. Okay. It will interpolate through all the points and it will run. So this is one thing that this type of robot can do. This is known as a lead through programming. Lead through programming, or there are many other names to it. So this is something. So this is a cobot called as KUKA IVA. This is just 5 kg payload capacity. We can pull even more now. 20 kg का झोला मम्मी उठवाई करना बहुत अच्छा So this is one example. This is lead through programming. Okay, let me go back. So this is what is the beauty of having a gravity compensations, and compensation is only due to the static forces due to gravity. Only gravitational force are compensated. So any external force can make it move, right? And robot behaves as if it is floating in the space, whatever I have said. Lead through programming is just one example which this allows. If you are gravity compensated, you can do this, and mechanical techniques are used to reduce the joint torque requirement at the joint. There are many other mechanical techniques which are there. Sometimes robots are compensated. If I'll show you a picture of industrial robot, any arm will have a counterbalance at the end. Counterbalance लगा सकते हो? If it is arm which is only at the front, you can have this arm extended backward with some kind of load. गेट में देखा फाटक रेलवे का याद आया so a small security fellow can just release the rope and it goes up. It is very heavy, you know. लोहे का बना होता है इतना लंबा rod. You can simply release the rope and it goes, right? Why? Because it is compensated with some kind of weight. So in this kind of robot, it is not there. But in case of industrial robots, normally they are gravity compensated in a similar way. But it is not always possible to do so because it is very complex thing. Every place is different. Maybe at one place you are able to do so, but in all the situations you cannot do that. So it is not always possible. Sometimes it is spring compensated. Spring are there, dampers are there, counterbalance is there. So there are mechanical ways of doing this also. So that is there in case of industrial robot, right? And implemented using various force control algorithms. You have algorithms that exactly calculates how much torque is going to come at this location due to gravity. You feed your motion, you feed your motors with exact that amount of torque because it has the joint angle sensors at each joint. So it knows its state. रोबोट नोज इज स्टेट है ना हर पॉइंट पे उसको पता है कितना ग्रेविटी फोर्स आने वाला एग्जैक्टली दैट अमाउंट ऑफ टॉर्क इज फेड एंड इट इज कॉम्पेंसेटेड राइट ओके there are control algorithms like stiffness impedance admittance hybrid controllers which are we'll talk about this don't worry okay okay this is one this is demo that I have shown okay I'll just drop this mathematics here this is simple physics how we calculate gravitational torque for any state of the robot. It is not just in a planar way, it is in a three-dimensional space. If your robot is going, what is the torque that is going to come? It is not using simple engineering mechanics, D'Alembert principle or Newton-Euler equations, you can get it. It is done using vector matrix approach over here. You can, if you, I am just scrolling it, video will be there. You can just watch it later, pausing it at different points. Okay, but it is there published also, various journals. I'll refer them also. You can always PhD MTech students can always go through that. They can come to me also. Okay, so I am skipping this one. If at all time permits, you are interested, we'll come back to it. So this is there to calculate the torque vector for all the joints for any state of the robot. Okay. What this offers me? There is some property which is known as a programmable compliance. Before we talk into the theory of it, let me just again show you one good video. Okay. Programmable compliance. So the end effector now behaves like a spring. What did you see just now? Compliance was 5,000. Now it is 300 Newton per meter. So it is like a spring. Stiffness can be varied in Cartesian space. It behaves exactly like a spring. These videos are there on internet. You just go to my channel. I have created a playlist of all these videos. Right. It is not my videos which are very much censored. So you see, and same compliance can be different in different directions. So every direction you have different compliance. You can do that. This type of algorithms are there. Controller architecture are very well published. So I'll share all those papers also. Okay, so this is one. Okay. Okay, so this is what is programmable compliance for different positions. So stiffness along any direction in the frame which is set can be controlled. And frame can also be changed, you know. It is not necessarily it is a frame which is attached parallel to the robot's frame. You can have compliance. You can define compliance arbitrarily in space. That means your orientation can be different. Damping along any direction is also there. What is damping? Higher is the velocity, higher is the force which is generated to oppose that force. Hai damping force. Stiffness is higher is the displacement from the mean position, higher is the force. Spring. Damping is higher is the velocity, higher is the force. Thoda the difference. Okay. So that is damping. You can even control the damping along each direction, right? Force to be applied in addition to spring damper model. Okay, force which is generated, it is based on the spring damper model which is there along each Cartesian workspace. Cartesian coordinate geometry पढ़ेगा, बस उतना ही है, उससे ज्यादा कुछ नहीं है, ठीक है? Additionally, you can set the stiffness and damping of the redundancy degree of freedom. You have redundant robot. This robot is a redundant robot, right? Why it is redundant? This robot is a 7 degrees of freedom robot. How many degrees of freedom your arm has?
Six.
कितना है?
6 है.
6 है क्या? I can take any object in space in how many ways? 6 ways.
6 ways.
End effector can reach 6 ways, but this robot, if it is redundant, it is known as a pose. Pose is position and orientation. Although your end effector has got 6 degrees of freedom for position and orientation set, right? So it is a pose which it can attain. For a given pose, you have infinite number of solutions. I can hold this bottle, right, in a way, and then I can move rest of my arm without even changing the position and orientation of this. So it is a redundant arm. Redundant arm. Why? How many degrees of freedom does this arm have? Start counting. This joint, type of joint.
Ball and socket.
Spherical ना? देखा है आरती? ऐसा कुछ होता है ना? बोन सॉकेट में घुसा हुआ है.
Ball and
ना? ठीक है, यहाँ पे 3 degrees of freedom. यहाँ पे कितना है? Elbow.
2.
It has only one.
One.
It has one degree of freedom. ठीक है, it can only twist किया तो गया. ठीक है, don't twist. Okay. Now wrist. Wrist about this way. Wrist can go in
2.
देखते जाओ. One, then 2, and then 3. With respect to this, you have additional 3. That means 3 intersecting axes are here. All the 3 axes are intersecting at a point that is known as wrist center point. Right? Wrist center बोलते हैं. And you have 3 degrees of freedom here. So 3 here, 1 here, 3 here. Palm has got 7 degrees of freedom. So that is the reason to obtain 6 degrees of freedom as an output, you have 7 degrees of freedom as an input. So it is redundant. It has more number of joints than required. Right? So it has infinite solution. To go to a particular place, you have infinite solution. Right? Right? Industrial robots को अगर घड़े के अंदर से ग्लास निकालना होगा, it has only 1 or 2 solutions that makes it go there. It will break the pot and it will get in. 7 degrees of freedom can get in like this. Right? So that is the beauty of it. It can defuse a bomb. Right? It can get कार के सीट के नीचे से बॉम्ब निकाल सकते. Industrial robot नहीं निकाल सकते. So that is the reason this kind of robots, redundant arm robots, are very popular in those applications. Okay, so this is one application. We'll talk about redundancy later also in this slide. Okay, so stiffness and damping along all the 7 joints you can control. You can control joint stiffnesses, and finally you can control the Cartesian stiffness. Joint में stiffness को control करके end effector पे stiffness को control करते हैं. You have 7 things to control. 7 stiffnesses, 7 damping to control at joint level. So at joint level you do it, you get it at the end. There is a relation between them that is done by controller architecture. I'll show you that, a picture of that. Won't discuss much. Okay, so that is what it is doable with this kind of thing. Limitation in maximum force at the end effector. You can limit the maximum force which it can apply at the end effector. End effector here is this. Okay, where you fix your tool, right? So you can limit that force. Maximum Cartesian velocity can be fixed as well. Maximum velocity with which, let's say your robot is capable to go at 2 meters per second, you can limit that also to go to, let's say, 0.5 meters per second only. Right? So that limitation is doable. It can detect a fall also. If at all your robot is falling against gravity due to certain kind of failure, it will detect because it can detect the maximum velocity. If it is freely falling, velocity will be more prior, right? So it can detect that fall and it can apply the joint brakes immediately, right? So it is very very safe that way. Okay, and then Cartesian path deviation, because it is compliant, this feature should be there. Because it is compliant, normally they deviate from the path, है ना? पाथ से थोड़ा थोड़ा डेविएट हो जाता है, थोड़ा स्प्रिंग टाइप का बिहेवियर है, इट इज नॉट दैट स्टिफ रोबोट. So that is taken care of by the controller very well in this type of robot. That has to be taken care of. So these are some additional things that should be there. Okay. Next is arbitrary reference compliance. Again, I'll show you a video that will speak better. TCP, tool center point. TCP is tool center point. It is compliant. Behaves like a torsional spring above that point. That point can be changed, can be placed anywhere in the space. Arbitrary reference compliance can be programmed. These things are very, very interesting, you know. And these robots, they don't publish this. You have to find out the mathematics behind. They will give you these features in their teach pendant, but I would suggest any robotics enthusiast to go through that manual. Manual is freely available. What all features does it apply, give you? It is not documented, not published, but it is there in their teach pendant. They allow you doing this. How is it that possible? Right? Just try to find it out. If at all you are familiar with DS parameters, mathematics, everything, but you know how this is done? No. So you have to find it out. Otherwise, they will never come when you can make a robot. Right? You have to find out. They haven't published it. Right? So this is what is offered by this robot again. These are some of the offerings. Okay, I haven't talked about how they are offering it. Okay. Okay. Frame can be placed anywhere in the arbitrary location that I have shown you. One such example is remote center of motion. That is in case of surgical tool. Let us say if it is a laparoscopy tool which gets into your skin. This is your abdomen. Okay. You have inserted a laparoscopy tool. You are operating over here. You are doing some task inside your abdomen. This space is inside your abdomen. But this point should be stationary. When you move your robot, this point should not move. It is a point where you have penetrated the skin. If you move this point, क्या होगा?
The penetration will increase.
इंसिजन जहाँ छोटा सा है, ऐसे तो पूरा है ना? समझ रहे हो क्या हो रहा है? So that point should be stationary. This is just one application. When you want a remote center of location, which should be stationary, and it should be compliant about that. You are moving, you are taking this point in consideration. Tip of the surgical tool does the job. Right? Okay. Next example is programmable path compliance. This is very similar to the example that I gave you for mobile robot, Durga Puja Pandal wala example. You can, it is very much analogous to that. Programmable. Okay. Okay. This time you have set the stiffness along E direction, but the robot is okay. It was 5,000 Newton per meter. This is 300 Newton per meter. A bit of compliance is there. Robot is moving. This is 100 Newton per meter. He is able to stop quite a bit, right? This is one application. You just see what it is able to do. This is an arbitrary path. With respect to robot, I don't know the path. What I'll do, I'll simply command my robot, just run it once again, take it to the end. So you see, you just allowed your robot to be commanded to go from this to this. So any deviation in between you don't know in your own reference frame. So you cannot command your robot to go there. Left to right, just go from left to right. The rest of everything will be taken care of by compliance along that direction. Compliance along that direction. So without knowing an unstructured environment can be handled with this kind of robot. Unknown environment can be handled, right? So that is easily doable. This is one. Okay, so these things you are getting out of it. So for the safety of human in workspace, these are some of the application. Collaborative manipulation of multiple robots. Multiple robots, if they are handling a single thing, so one of the robots, let's say the dragging of cart in a workspace, I gave you one example, right? दो लोग मिलकर के एक cart को carry कर रहे हैं एक दूसरे दूसरे को. One of them has to be compliant. If one is very strong, he becomes the master, other one becomes the slave. Right? You need not to be very accurate in your position to precisely maintain the distance between those two handling points. That distance is not changing. You are not bothering about that. Geometrically, if that changes, your cost will be torn apart. Right? That should be torn apart. But that is taken care of by the compliance in your arm. So that kind of task can be done by this sort of path compliance. Robot is moving, but it is compliance along any orthogonal directions, Cartesian direction. Okay. Earlier days, it used to be done by remote center compliance, a device, a passive device, which is fitted at the end. So let us say you have to insert a peg within a hole. So if there was some tapered surface. If you come in contact at this angle, immediately it gets directed towards the hole. And this is the passive mechanism, which is spring-like structure, and it is compliance along this direction. It is not compliance along this. Right. So this tool was known as a RCC device. So this was the earlier way of doing similar thing. Okay. Okay. So ease of programming of unknown surfaces. I have shown you similar video. So robot assisted assembly. This is a kind of assembly, a peg in a hole task that I have shown can be done with this. Okay. So this is simple mathematics that takes care of this. If somebody is familiar, this is Jacobian transpose. External wrench gives you the necessary torque to do this. So, okay. So this is a kind of controller which is there inside. It is very, very complex. Use lot of mathematics gets in. But don't worry. If you follow just kinematics, 90% of the things are answered. At least Jacobian transpose. Jacobian is a relation between the joint velocity and the end effector velocity. So it is just that. This is the external torque if it is coming. So it is very complex. I won't talk about the mathematics of this. Okay. If required, you can copy one of my publication also that is there. Okay. So taking into time into consideration and the knowledge that it requires and diversity of people sitting out here, I'm skipping this. But yes, if you are interested, you can communicate with me. I'll share this. Okay. This is quite simple, not difficult though. Okay, this is called as an impedance controller. Impedance controller, which is published by Zheng and Imani in 1997. This is the one. Okay, and then all the examples that I gave you, it uses this type of controller architecture. Mostly things are very much in kinematics. Only thing where you have dynamics is within here. That is sitting here. Dynamics is all coded there. That is there in the robotics. Okay. Okay. So control equations contain all these parameters that is there. Okay. You can take snapshot and share this slide once again after this presentation. You can go through that. There are few special features also. So apart from the features that you saw just now, that this type of robot can offer, that is why it is possible to do this kind of job. There are few other things which takes care of the safety aspects and the certification aspects of this kind of robot. One of them is force triggered stop. If at all it collides, it will not further move. Okay, it will just stop there. That is known as a force triggered stop. There is one more thing which is there sometimes. It is force triggered start also. Why a robot should have there? Hey robot, start moving. You want to tap your robot and make it move. So that is also doable. If it can detect any sort of vibration in its any of its surface, how it can do it? Any common sense answer to this?
Vibration sensor.
If I am tapping, this robot is able to sense.
Vibration sensor.
Not necessarily though. You don't have any vibration sensor. You saw the joint architecture. There was no vibration sensor in between. You have torque sensor at the joint. Right. So these joints, if you tap, that torque vibration will come, no? That will let you know. Which link you are tapping, that also you can come to. All AI ML guys should not get in. If you are tapping it twice, you are tapping in this link or whatever link. So accordingly, the torque sensors will show up, right? And you can detect precisely where you have tapped. Okay, you are shouldering my arm. No, elbow. So you can precisely find it out, right? Based on the torque sensor value. And you can make your robot tap to start, tap to stop, and many other fancy things. And normally not required. So free fall detection due to speed monitoring, that I have told why it is required for the safety reasons. Workspace protected spaces. It was there in older robots also. You can confine your robot to get into some workspace. Let's say your joint, this joint can go. Let's say you have a base joint, your robot is there. You don't want, because you have a table over here, you want your robot to operate from here to here or here to here. Okay, so you can safely monitor that angle. You can exclude that motion from your motion list. You can have that in joint space. You can have that in Cartesian space also. Cartesian block, you can always define in space. Your robot will never go there. In case of cobots, which has full knowledge of its geometry also, even your arms will not go there. Problem with the earlier robot with the end effector sensor was it had a force sensor which was at the wrist. It can detect the forces, can do the force-based assembly task, but only after the wrist. If your link gets entangled anywhere, you're gone. It won't even come to know. Because your sensor is sitting here, it can sense anything which is after this, not before this. So that was the problem. But with this kind of robot, you have torque sensor at the each one. You can convert that torque to the forces that are coming in. You know the physics of it, right? So that is how it is done. Okay, and external surfaces is mostly made using plastic. Mostly these kind of robots are made with plastic exterior surface, so that least amount of damage can happen. Rubber or aluminum, lightweight aluminum structures are there, so as to reduce the moment of inertia due to and any momentum causing damage. Okay, so that is there. May have additional sensors to detect human in the proximity. If at all any, yes.
Then you said that this robot uses the Cartesian coordinate system, so it must set an origin so
Yeah.
that it can move forward. So how does that happen, sir?
See, a robot has got many frames which are defined. You have few standard frames. Please sit down. Few standard frames are, one is universal frame that is sitting at the corner of the workspace. You have n number of robots which are placed in the workspace. In industry, you don't just have one Cartesian system. You have a universal coordinate system. Next coordinate system is about its own base frame, where it is grounded, the ground. So that is one. That is the frame, Cartesian frame X, Y, Z. There is transformation between that and that. Okay, universal frame and the robot base is translated as well as oriented little differently. Then comes your end effector frame, that is at the tip of your flange somewhere. Tool flange is there, where it is actually doing some job. You have object frame, you have base frame, that is the workspace frame on which robot is working. So you have different frames which are kinematically linked. You have to have complete knowledge of frames as well as relation between them. Your robot rotation with respect to universal frame is calibrated and calculated before you put your robot to the use. Once you mount the tools, your frame has changed. If it is a welding tool, it is somewhere over here. If it is a clipper, it is somewhere over here. Right? So frame changes is calibrated. That is known as TCP calibration, tool center point calibration. You do some sort of identification experiments to find out those frames. Again, industrial robots, they give it for free without documenting how it is done. It is left for all the students, researchers, PhD students to find out what is the mathematics which made it possible. Hmm? That doesn't mean I am exempted to tell you why it is happening. Okay? So it is covered in few of my lectures which are already there on YouTube. This topic is not closely related to robots, so I am excluding it. But definitely you can follow me on my channel also. Very soon in NPTEL course also which is going to come. I have covered this topic explicitly. That makes this course quite unique as compared to many other books which it has covered. Okay. So definitely I would suggest you go through that. It is very, very interesting. It is kinematics which is mostly interesting if it is industrial robots or any industrial robot, even if it is a cobot. Why? Because most of the things are not documented, not taught in the book. It is not there in the book. The question which he has asked is very good question. He has asked only about the places how a robot base is calibrated. And even if you put a rotary turntable, robot is able to pick up the object from rotating turntable. How is it doing it? Sometimes base is not fixed. Base is moving on a rail. एक रेल के ऊपर रखा हुआ है robot is moving like this, doing something, again it is coming back, doing something. Okay, so even this base calibration, robot base calibration is required. Transformation of this base with respect to the linear rail as well as to the universal frame. Those relations are done by some kind of experiments. So all those experiments are listed in robot manuals. How they are done, I have covered it in TCP calibration and calibration chapter of my NPTEL course also going to come very soon. But yes, I will be sharing that. Okay. There are few papers which is documenting a few of those. But yes, this is very important question. Okay, so you may have additional sensors to detect human in the proximity. Sometimes these robots has got proximity sensor. If you come closer, it will slow down. If you come further closer, it will stop. It detects human in the proximity. That is what is making it a cobot as full sense. So you don't need a cage. Hai. So yes, smart automation features include compliance to Industry 4, IoT and all is there. Nowadays, as soon if at all you fail in an attempt, you come to know you're sitting remotely somewhere. See, as soon as you pick up, you have torque sensor, you will come to know how much force has come. If you fail to lift an object, immediately you will come to know whether it has failed or not. Normally, in earlier robots without any sensor, you won't come to know. You can just do a mock. Go there, flip it, nothing came in, just came back. Again, you went there and left something. Sometimes you fail, sometimes you doesn't fail. You don't fail, right? So, but in case of cobot, you can be very much ensured. Yes, I have failed. I won't do a mock. I'll repeat again, try it again. Right? And that failure attempt can now be communicated to the remote user. Using your sensors, can now know. So these kind of robots are connected to internet. They are unsafe also. So that is the reason that is a different kind of internet protocols which are followed in the industry. So that movies mein hota hai na, they hack your system, do something. So that cannot happen in the. That is not natural. Right? Industry 4 allows those kind of communication, and these robots are all complying to those IoT 4 and all those kind of stuff. IoT they call it. Industrial IoT. That is a similar protocol to IoT. Okay. And spatial trajectory like this also allows not just taking your robot to a position trajectory. Position trajectory, like say you are doing some welding operation. You have given a path. You have to go like this, do this, done, do this. So it is a curve that it is following. This is a set of position varied over a period of time. Why time is important? in any operation like gluing, welding, painting, it is not only position is important, it is also trajectory which is important. Time. Why? Common sense. Why? Time is very important. If you are not just supposed to move from a point to point, you are very specific about the velocity with which it is moving along the surface. Why? Because let's say you are doing a welding operation, if you stop anywhere and keep doing welding, what will happen? Huge amount of lump will be deposited there. Gluing may be where it is continuously dispensing adhesive. If you stop it or go a little slower at a particular region, you will deposit more number of glue over there, more amount of glue over there, is it not? So that is the reason. So you have to complete, do the trajectory. Time is very important, right? So position trajectory and as well as it also has a force trajectory. What does that mean? Each and every point, how much is the force? What should be the direction of force you want to be compliant? Let's say I have told normal to the surface, I want to maintain 10 Newton. Okay, it has a very different meaning. So, because normal is changing at every surface, it is curvy. So, normal is like this, like this, like this, finally like this. Is it not? So, normal is changing, so is your trajectory changing. So, force trajectory is also very important. You are not just controlling position trajectory, you are also controlling the force trajectory. So that is what force vector is changing at each point of your trajectory location. So that also can be commanded. You see, a huge amount of flexibility is there. It is a magnificent robot actually, very good robot, right? So it can also detect, it can make you some standard type of oscillations, force oscillations. So normally when we assemble, we do assembly using oscillation. Have you ever noticed it? Pushing a key in a keyhole, what you did? You oscillated and you inserted. You kept on finding the constraints and finally you are able to do it. So what you did is not a position oscillation. You gave a force oscillation. So that if at all there is any constraint over in any direction, it stops there. It doesn't break it. It stops there until unless you see stoppage is all over, you just pushed it. You just pushed it, right? So that is how you did it. You just revise what you have done plenty number of times in your life. You will understand the cobalt, right? So that is this type of oscillations are possible. Force oscillations are possible with cobots. That is sine wave, spiral, messages. This kind of things are there. These help in handling hole search. Sometimes to handle jamming. If at all something has jammed, you just vibrate it and it goes. Assembling a gearbox, you say. गियर के ऊपर गियर को असेंबल करोगे, you just vibrate it, it goes. Huh? Okay. So yes, there are many other things to teach. This is one just last video. I hope I am not running late. 33 हो गया. Just one video is there. So kinematic redundancy. This will just thrill you like anything. I don't know if you get.
The third one.
This is what I meant by infinite solution. Kinematic redundancy. This is strictly in its place. Rest of the robot is able to move about that. 7 degrees of freedom can include those. So this is what is also there with cobots nowadays. It can give you infinite solution for a given pose, right? And that is what is there in most of the cobots, which say they are 7 degrees of freedom. It is very difficult to solve this kind of kinematics also. Because you have infinite solution, you have to be intelligent to pick one of them based on the least power requirement or maybe constrained workspaces you are doing, right? So these are few terms. I'll quickly skip this one, but this is one of the most interesting things. Okay. Okay, this is Lissajous curve. So we did some experiments. I won't go deeper into it. So this is one of the cobot. We made it do some peg in a hole task. This was a bath project that we were given. to handle a nuclear pellet insert in a hole. This was again a vision challenge was also there. It was kept in a bin filled up with black. L by D ratio was very poor. Length and diameter was same. So if you look from the top, you see a square. You won't come to know which side to hold. Right. So, and again, it was in a black background. Nuclear pellets are black, and if it is kept in a bin, so it becomes black in the background also. So you see how difficult it is to do. And then you have to pick one of them, insert in a hole without breaking. So we used cobots for that reason. So this was force oscillation in air, force oscillation, those kind of stuff we did. This is a set of major makers who are making industrial cobot. So the first one is 35 kg payload capacity. I have never came across that. It is very difficult to make that. 35 kg and still compliant. Still can feed the forces. This is very, very difficult. And Anuk is a company who is making it highest payload capacity. Like robot now, even Kuka LBR comes very closer now. Earlier it was 5 kg, now it is 14 kg. So this is a huge list of companies who are making such robots. Not all of them are certified. Not all of them. Apart from industrial certification, position and repeatability, they may not be certified. So before you buy one or use one, be sure what all certification it has. Then only you get into that workspace and take some risk. Right? Don't go by the claim of the manufacturer. Even if you are a UG student, your boss will say, okay, this is a cobot, get in. Don't just blindly believe. Right? I have seen many robots, they have not even have a repeatability test done. Forget about cobot test. मैंने ISO certification को list किया है ना, just go through that. ठीक है? So for PG, PhD students, these are some research directions you can look in if you want to work with cobots. So I was one of the students who have worked in industrial robots which are compliant. Many videos to share, you can see them on my YouTube channel if you get some time. Okay, so these are some directions and these are some of the my publications which can help you. Okay, important literatures, how it has evolved. Okay, these are the labs I want to acknowledge where all these videos I have acquired and some funding agencies which are here. Okay, and that's all. Thanks a lot. And this is the course which is going to come in SWAM portal this year. I would suggest you go through this. If I am teaching well, you can prefer that. Right? So this is going to come this July only, no? 24th of July, course is starting. Registration is on. I don't know how many have already registered. Okay? So that's all. Thanks a lot. Any queries I can take up. So all the calibrations now, there are few things that I have covered in this course, which is not there in regular testing. That is practical implementation of industrial robots. You have to do a lot of things apart from theory. And most of the time books remains wherever it was, in the library. Okay, you have to do something else. Those else things are also covered. That is calibration, the process which he has doing. Any other theories we can handle. Okay.
Any questions? Please ask.
Aduga is my company which I am running on. It is a company which makes parallel robot moves. You can go through this website also. What we are doing it. YouTube, that is my channel. You can find a few of you have asked DS parameter if you are going to cover or not. It is already there on my YouTube channel. I have covered DS parameters very well. Right. So I have got a good feedback of my earlier course that is recorded and online. It's already there online. Just go through that. I think it will be helpful. Engineering mechanics field. अब बोलो.
Any questions? कुछ भी आप लोग को सबसे पूछना है?
Could be.
Anything like
robotics, life, philosophy. I am good at speaking about philosophy also. Teachers are always good at it.
Thank you, sir. The session was really very nice and very interactive, sir.
Interactive नहीं हुआ आगे बढ़ो आगे बढ़ो
So definitely, sir,
start करो
so I'd like to call upon coordinator of this event, Dr. Jain Kumar sir, for giving a token of gratitude to sir with a watch and